Okay, good morning, everyone, and welcome, ladies and gentlemen, to our third session of the virtual conference. And I hope you can see my screen okay. Our third session will be on the Manifesto on Uncertainty with Professor Denoeux and Professor Goldstein. We have a schedule of the coming sessions for the weeks to come as well. Our next session is actually on Wednesday, on the 17th of February. And the one after that will be on the 3rd of March. And the other dates are still to be confirmed. There's some on the 12th and some on the 17th, but there's another 2 talks that we still have to arrange.
Francis,
Yeah.
We may not be able to see your screen. Can everyone see the screen?
Yeah. Now okay. Now it's okay.
There we go.
Sorry, there. I moved it to the other side so it was aligned with webcam, because otherwise it looks like I'm moving away. So apologies for that if it looks like I'm looking at something else. So the first talk will actually be random fuzzy sets, a general model of epistemic uncertainty with a Q&A, and that will start any minute now, and that will last for an hour. At 11 o'clock, we'll be listening to Professor Michael Goldstein's talk on the basic principles of reasoning about uncertainty, a subjectivist approach, plus Q&A, and that'll be followed at 12 o'clock by an open discussion where we expect to see some fireworks between these two academics. And our question will be, can we agree on anything about handling epistemic uncertainty in engineering? So our first speaker, Professor Thierry Denoeux, and his talk on random fuzzy sets. I'd just like to say a little bit about Thierry Denoeux and his background. So Thierry is a full professor with the Department of Information Processing Engineering at the University of Compiègne in France. He's a senior member of the French Academic Institute, and his research interests concern reasoning and decision-making under uncertainty, and more generally the management of uncertainty in intelligent systems. He's done many contributions in the theory of belief functions, in applications with statistical inference, pattern recognition, machine learning, information fusion too. He's published over 300 papers in the area, and he's the editor-in-chief of the International Journal of Approximate Reasoning and the Journal Array, and associate editor of several journals, including Fuzzy Sets, Systems, and International Journal on Uncertainty, Fuzziness, and Knowledge-Based Systems. So I'll pass you over to Thierry, if you can, and share your slides, and we'll get started. Thank you very much.
Okay. Okay, thank you, Francis, for this introduction. And so I'm very happy to be given the opportunity to participate in this very interesting virtual conference on epistemic uncertainty in engineering. So today I will talk about random fuzzy sets, which I will try to show can serve as a kind of unifying model that somehow encompasses different models of uncertainty used in computer science and engineering. You may notice that I changed a little bit the title of my talk. Initially, I used the expression epistemic uncertainty because it was a topic of the conference, but now I removed epistemic because in some way, I would argue that uncertainty is always epistemic because uncertainty is lack of knowledge. And of course, I'm aware that in engineering, epistemic uncertainty is often used as the opposite of aleatory uncertainty. So I will try to propose a definition of aleatory uncertainty. To me, aleatory uncertainty is uncertainty about the characteristic of an individual that is only known to belong to a population with known distribution. For instance, drawing a ball from a known containing balls of different colors with known proportions. Okay. Or to take a topical example, assume John has COVID, and all we know about John is that he lives in the UK. And we know that 3.5% of COVID patients in the UK need hospitalization. Will John need to be hospitalized? So here we have generic knowledge about population, and we want somehow to transfer this generic knowledge to one individual in that population. So this is, of course, an ideal situation, not so often encountered in practice, because usually the exact frequencies in the population are not known. And sometimes there's only one element in the population. Think of the next presidential election in France. It will happen only once in exactly the same conditions. but yet aleatory uncertainty is at least useful as an approximation. So to reason and to make decisions under uncertainty, we need mathematical models. And as you know, several such models have been proposed in different fields, actually in statistics, computer science, engineering, economics. And here I would like to emphasize that to me, these models are just tools. And here I like to quote this famous sentence from George Box: all models are wrong, but some are useful. Okay, so models essentially are more or less useful. And I think these models of uncertainty must be defended based on their ability to support and justify sound conclusions, and also on their ease of use in practical applications, which I think is important from an engineering perspective. So in this talk, I will mention a number of these models. I think they're the most frequently used ones, at least in computer science and engineering. So I will start with what I think are the two classical models, which are probability theory on the one hand, and what I call Boolean possibility theory on the other hand. It's just a set-based approach. Then I will review two more recent extensions, which were proposed in the late 1970s. Possibility theory based on fuzzy sets, an extension of the notion of set, and Dempster-Sheffer theory based on random sets, which random sets extend both sets and probability distributions. And then finally, I will arrive at this general model of what I call epistemic random fuzzy sets, which I think is actually needed to, let's say, describe most of the types of uncertainty that we encounter in engineering and computer science. Okay, so let me start with the classical models, and first with probability theory. Okay, so of course we all know about this. I will here just introduce some notation. We consider a question Q of interest and a finite set theta of possible answers to that question, one and only one of which is true. So here I will assume that set theta to be finite, just to avoid mathematical intricacies, but all I'm going to say can more or less easily be extended to infinite spaces. So let us denote by P of A the degree of belief, our degree of belief that subset A of theta contains the true answer. By convention, we measure degrees of belief on the scale between 0 and 1. And probability theory essentially makes two main assumptions. The first one is additivity, which in particular implies that the degree of belief in the complement of A is 1 minus the degree of belief in A. And the second, let's say, important component is Bayes' rule of conditioning, which is a rule to update one's beliefs after we receive a new piece of information. Okay, this model is actually quite natural in case of aleatory uncertainty. For instance, assume that we know that a ball was taken from an urn in which 40% of balls are black. What is our belief that this particular ball is black? So here we have a problem in which the question Q pertains to some characteristic of an individual that is only known to belong to a population in which possibility theta k is present in proportion pk. Okay, so we know the proportions in the population. And so what we can do is to equate our degrees of belief with the proportions in the population, which of course gives us a probability measure. Can we extend this model to other types of uncertainty? And many people, of course, will argue that indeed we can. And probably Michael will argue also for this thesis later in the next talk. And I think there are indeed good arguments to answer positively to that question. There are also, I think, good counter arguments. So I will not have time today to discuss in detail these arguments, but maybe will come up in the discussion. Here, I would just like to mention some difficulties that arise when describing states of complete or near ignorance with probabilities. And I think the best we can do for this is to use the principle of indifference, which was proposed by Laplace, which states that in the absence of any relevant evidence, agents should distribute their degrees of belief equally among all the possibilities under consideration. And here the problem I see, and maybe we can have a discussion with Michael after our talks, is that this equal distribution of beliefs depends on the granularity with which we define the different possibilities. And I will illustrate this point with the Sirius paradox described by Schaffer. Assume the question is there life around Sirius, around the star Sirius? So we might argue that there are two possibilities, either there's life or there's no life. And applying the principle of indifference, we are led to giving probability of 1/2 to both possibilities. But actually, if there is no life, it can be that either there is no planet or there is a planet but no life. So that we can split this possibility into two, so let's say, finer possibilities, so that now we have 3 possibilities in total. And now the principle of indifference gives a probability 1/3 to each. Okay, and so we see that we get a different answer depending on the degree of granularity with which we define the possibilities. And the point is that this degree of granularity is often more or less arbitrary. And so in situations of near ignorance, the degrees of belief you assign to different possibilities has also some arbitrariness. So I think that such paradoxes, there are other ones like the famous also wine and water paradox, appear when trying to, let's say, somehow squeeze set-based information into the probabilistic formalism. And I would argue that there's no necessity to do so. And actually there's another approach, which is also, I think, quite widely used, is just work with sets. So actually when the evidence points to a set of possibilities, an alternative, instead of trying to, let's say, probabilize that set, is to keep that set, just that set, as a representation of the evidence. So knowing that the truth is in F, a proposition is then, A is then said to be possible if F intersection A is non-empty, and it is certain if A contains F. So that we can define 2 mappings from the power set of theta to the set 0 and 1, a Boolean possibility measure that assigns 1 to each subset if subset A if A is possible and 0 otherwise, and a Boolean necessity measure that assigns 1 to set A if it is certain and 0 otherwise. So that in this approach, we no longer have a single additive probability measure, but we have 2 mappings taking values in 0, 1. And these mappings verify these probabilities. So I will briefly go through them. So the first equality here states that A is possible if the complement of A is not certain. The second equality says that A union B is possible if either A or B is possible. And the third one states that A and B is certain if both A and B are certain. So here the second equation expresses a probability that is referred to as a maxitivity probability. Okay, so we have 2 measures, one of which is maxitive, and the other one is dual. Okay, and in this approach, updating is just set intersection. If we have 2 pieces of evidence that point to 2 different sets, F and G, of possibilities, then we just take the intersection. So what plays a role here of base conditioning in this approach is just set intersection. In engineering, this set-based approach is applied basically with intervals. And interval analysis is one of the important approaches, I think, in numerical computations in engineering. So the principle here is to put bounds on all observations and model parameters and to propagate these bounds through numerical equations. So the advantages here are simplicity, because it's often much easier to propagate intervals than to propagate, say, probability distributions. For instance, if we have bounds on X and Y, we can easily derive bounds on the at X plus Y, X minus Y, and so on. And second, the results are guaranteed in the sense that if the initial bounds are correct, interval analysis guarantees mathematically correct results. But working with sets also has some limitations. First, this approach does not allow us to express doubt. And as a consequence, it is often too conservative. If you design these bounds to be 100% sure, then you need to be very conservative, to the point that the result might not be even useful in the end because they might be too imprecise. Another limitation is that the available information is sometimes too imprecise or vague to allow us to define precise bounds or sharp boundaries. And this is, for instance, the case when we try to convey, to describe information conveyed in natural language using such words as small, large, old, young, roughly, about, and so on. So these limitations have motivated some extension that were proposed about at the same time towards the end of the 1970s. And I will first briefly review the first one of those, which is possibility theory. So possibility theory is based on fuzzy sets. The idea of a fuzzy set is that of a set with an unsharp boundary. And formally, we can define a fuzzy subset of a set theta as a mapping that assigns a membership degree between 0 and 1 to each element of the set theta. And this fuzzy set is said to be normal if there is at least one element in theta with full membership to the fuzzy set. So here we see an example of a membership function or a fuzzy set that captures the concept of middle-aged person. Okay, so now assume that you receive vague evidence described by a normal fuzzy subset F tilde of possibilities that you can interpret as a flexible constraint. For example, you get a testimony that tells you that John is middle-aged. Okay, this information can be completely reliable, and you trust the witness, but okay, John being middle-aged puts a flexible constraint on John's age. Okay, it tells something about John's age, but it's not the same as giving exact bounds. So given such evidence, a subset A of possibilities is all the more possible that there is some element theta of A that satisfies the constraint. And A is all the more certain that all elements, all possibilities outside A fail to satisfy the constraint. So that we can quite naturally define degrees of possibility and necessity using these equations here. So the degree of possibility of the set A of the set A, given we know that, given the flexible constraint expressed by the fuzzy set F tilde, is a maximum of F tilde of theta for theta in A. And the necessity of A is a minimum outside A of 1 minus F tilde of theta, which is also 1 minus the possibility of the complement of A. Okay. So here we now have two mappings taking values in the interval 0, 1. So we have like a graded notions of possibility and necessity. Okay, so these definitions obviously generalize the corresponding definitions in the Boolean case. We still have this maxitivity property and the dual property for the necessity measure. And here another definition that is useful is that of a possibility distribution. So the mapping that maps each theta to its possibility, it's a point here mapping, is called the possibility distribution. And so obviously the possibility distribution is numerically identical to the membership function of the fuzzy set. Okay, so in this framework, how do we combine information? Assume you receive two vague pieces of evidence represented by two fuzzy sets, F tilde and G tilde, how to combine them. So here, assuming both piece of evidence to be reliable, it also makes sense to take the intersection. Okay, so we need a definition for the intersection of fuzzy sets, and we also need some normalization to get a normal fuzzy set. So there are a number of different definitions for the intersection of fuzzy sets. I don't have time here to review them. I would just mention that this operator shown here has good properties. It is a normalized product intersection. And so to compute the intersection of the two fuzzy sets, you just multiply, okay, these membership functions, and you divide, you normalize by dividing here the result by the height of the fuzzy set of the product, the height being the maximum membership degree. Okay, this operator, this intersection operator has some nice properties. In particular, it is associative. Okay, so here an important point is that we have seen that possibility theory is suitable for representing evidence expressed using natural language, but I would argue that it is also relevant for representing statistical evidence. And so assume that you have a parametric model here with some observation X and a parameter theta. After observing the data X, we can define the relative likelihood function by this equation. It's just the likelihood function normalized to be to take values between 0 and 1. And it has been argued by several authors, and I think there's quite good arguments for that. I will not have time to develop them, but we can come back to this in the discussion, that this relative likelihood function can be interpreted as a possibility distribution. So the notion of likelihood and possibility actually are quite close. And equivalently, this relative likelihood function can be seen as a fuzzy set of likely values of the parameters after you have observed the data. And we can just observe that here, that how do you combine two relative likelihood functions from independent samples? We, of course, combine them by this product rule. Okay, so we see that here, this product intersection rule is actually what we use to combine likelihood functions. So we'll come back, I'll come back at the end of my talk to this possibilistic, let's say, interpretation of the likelihood function. Okay, another extension of the classical models is Dempster-Sheffer theory, which is actually based on the idea of random sets. So what is a random set? A random set is obtained by considering a probability space, let's say omega, and a mapping gamma from omega to the power set of the universe theta. So you get a tuple that we call the random set. Okay. So this model can be used for different things. In some cases, it can be used to model actually the process of randomly generating a set. But here I will give more like an epistemic interpretation of a random set. Here, the meaning of this model will be the following. Omega is a set of interpretations of a piece of evidence. Okay, we assume we get evidence, and this evidence can be interpreted in a number of ways. If interpretation omega holds, the evidence tells us that the truth is in a non-empty subset, gamma of omega. We assume gamma of omega is always non-empty. Okay, so this is what the evidence tells us and nothing more. Okay. So if interpretation omega holds, the meaning of the evidence is that the set gamma of omega contains the truth. For instance, assume that a sensor tells us that a parameter of interest is in some set F, but this sensor is 80% reliable. So here we have two possibilities. Either the sensor is reliable or it's not reliable. If the sensor is reliable, and this has a probability 0.8, we know that the true value of the parameter is in F. If the sensor is not reliable, okay, we don't know anything, so we only know that the parameter is in theta. Okay, so you see that this such a multi-valued mapping, gamma, carries probabilities from elements of omega to sets of theta. Okay, so that what we get on theta is a probability mass function on the power set, actually. So we call this probability mass function on the power set, we call it a mass function, just a Dempster-Sheffer mass function. We denote it by the letter M, and it has the following properties. Of course, the sum of M of F for all subset F equals 1, and the mass on the empty set is 0. So here we have to be careful about the interpretation of M of F in that model. It is a probability of knowing that the truth is in F and nothing more given the evidence, because it is a probability that this is the meaning of the evidence. So each subset F with a positive mass is called the focal set. And of course, we get the two interesting special cases. If M has only one focal set, then it's equivalent to a set. And in that case, we say that the mass function is logical. And so we get the set-based model. If the focal sets are singletons, then M is said to be Bayesian, and it is equivalent to a probability mass function. Okay, so such a mass function induces two non-additive measures, a belief measure and a plausibility measure. So assume we know that the truth is in F, we have seen how we can define a Boolean necessity of any subset A and a Boolean possibility of A. Okay. Now, we don't know if the truth is in F. We have some probability M of F of knowing that the truth is in F. So we can compute an expected necessity for any subset A by this formula. And this expected necessity is what we call a degree of belief in A. And so the interpretation of this degree of belief is of a degree to which the evidence supports A. In the similar way, we can define the expected possibility of A by this formula, which is just 1 minus the degree of belief in the complement of A. Okay. And this degree of belief is interpreted as the degree to which the evidence fails to support the complement of A. Okay. So we have a degree of support in A and a degree of lack of support in the complement of A. So once again, we instead of having one additive measure like in probability theory here, we have two measures. Actually, one is subadditive, the other one is superadditive. Okay. So these two mappings are called respectively a belief function and a plausibility function. There's an interesting characterization of belief functions using this complete monotonicity property. Okay, so actually a set function is a belief function for some mass function M if and only if it verifies these inequalities for any integer k greater than 2 and any collection of k subsets of theta. So of course, if you replace this inequality sign by an equality, we get a property of a probability measure. Okay, so if a set function f verifies all these inequalities for all k, then it is a belief function, and we can actually recover the underlying mass function and the mapping from mass functions to belief functions in one-to-one. And again, we have these two special cases. If the mass function is Bayesian, then this belief function is a probability measure. That means we have equal signs here. And in that case, the plausibility function is equal to the belief function. We have only one function. And if M is logical with a single focal set F, then we get the Boolean necessity and possibility measures of the set-based approach. Okay, now how do we say aggregate or combine evidence in this framework? So here I will assume that we get two independent pieces of evidence, each one represented by a random set. So we have two random sets. Okay? So here, basically, we are going to consider each pair of an interpretation of the first piece of evidence and an interpretation of the second piece of evidence, and consider the intersection here of the multi-valued mappings. Okay. So for example, if we know that omega 1,1 holds and interpretation omega 2,1 holds for the second piece of evidence, then we know that the truth is in F1 intersection G1. Okay. There is a difficulty if the intersection is empty. For example, F1 intersection G2 is empty. So in that case, what that tells us is that this particular pair of interpretation that results in empty is in a contradiction, let's say, is impossible. So the independence assumption here we translate into considering the product measure, the product of those two probability measures P1 and P2, but we have to condition this product measure to eliminate pairs of inconsistent interpretations. So we actually consider this combined random set, where here we have the product probability measure, and we condition this product measure by the set theta star of non-contradictory pairs of interpretations. And so this combined random set gives us this corresponding mass function, which is called the orthogonal sum of mass functions M1 and M2. Okay. And this operation is called Dempster's rule of combination. Okay, so this rule, this operator has some interesting properties. It is commutative and associative. It extends set intersection in the sense that if you take two logical mass functions with focal sets f and g, the orthogonal sum is still a logical mass function focused on the intersection of f and g. And so Dempster's rule becomes intersection when applied to sets. And I think this is quite important, it also extends Bayesian conditioning in the sense that if you combine a Bayesian mass function with a logical mass function with focal set f, so basically you combine by Dempster's rule a probability measure with a set, then you have exactly the Bayesian rule of conditioning. Okay, now I arrive to the part of my talk about an even more general model, which is a model of random fuzzy sets, where here we are going to combine these two ideas, the ideas of random sets and fuzzy sets, and we naturally get random fuzzy sets. Okay, so here, as before, we consider that we receive some evidence that can be interpreted in different ways, and omega denotes the set of interpretations with probabilities attached to them. And here we assume that if interpretation omega holds, the truth is constrained by a normal fuzzy subset of theta. Think, for example, of a witness that tells us that John is middle-aged, but this witness is only 80% reliable. So if middle age is represented by a fuzzy set f tilde, we have here this mapping gamma star that maps reliable to f tilde and not reliable to theta. Okay. And so here this tuple of this probability space omega and this mapping gamma tilde is called a random fuzzy set. So this mapping gamma tilde carries the probabilities from elements of omega to subsets of theta. Okay. So that what we got now is a fuzzy mass function. A fuzzy mass function, m tilde, is a mass function with fuzzy focal sets. Okay, now we have fuzzy focal sets. And each mass assigned to the fuzzy set f tilde is interpreted as a probability that the truth is constrained by fuzzy set F tilde. And okay, if the truth is constrained by fuzzy set F tilde, we have seen how we can define the possibility and degree and the necessity degree for any subset A. Okay, now we have a number of different fuzzy constraints with probabilities attached to them. So we can define an expected possibility, okay, by this formula, and an expected necessity. It turns out that this expected necessity is still a belief function. That is to say, it's completely monotone. And the expected possibility function is a dual plausibility function. Okay? So this random fuzzy set model also generates belief functions. But here we have to be careful that the mapping from fuzzy mass functions to belief functions is now many to one. Okay, there are many different fuzzy mass functions that generate the same belief function. Okay, and Dempster's rule can be also generalized to combine independent pieces of evidence represented by random fuzzy sets. Okay, so here I assume that we get two random fuzzy sets. So here we assume that if, for example, this interpretation omega 1,1 holds for the first piece of evidence and omega 2,1 holds for the second piece of evidence, then we have now a fuzzy constraint, which should be the intersection of fuzzy sets F1 tilde and G1 tilde. Okay, so here we are going to use one of those normalized fuzzy set intersections. So to ensure associativity, we can take the normalized product intersection I presented before. And so now we have this combined random fuzzy set. So we take this mapping now derived from this normalized product intersection, and we take this product measure, which corresponds to the independence assumption. But now we have to condition this product measure by the set of non-contradictory pairs of evidence, of interpretations, which is now a fuzzy subset. And so this is a fuzzy set because now a pair of interpretation can be contradictory to some degree. Okay. And so here we need some definitions for how to condition a probability measure by the fuzzy set. I don't have time to go into the details here, but it's one of the paper I mentioned at the end. And so this combined random fuzzy set gives us a combined fuzzy mass function, which can be computed by this formula. So we can actually quite easily extend Dempster's rule. So we get a rule which is still commutative and associative, and it becomes the combination of possibility distributions by the normalized product intersection when applied to logical fuzzy mass functions, that is to say mass function with only one fuzzy focal set. So it extends, let's say, the rule of combination of possibility theory. And it also extends the conditioning of a probability measured by a fuzzy event, meaning that if we combine a Bayesian mass function with a logical mass function with fuzzy focal set F tilde, what we get is the probability, a Bayesian mass function that corresponds to the conditional probability given F tilde. Okay, so all this is quite consistent. And I think we have a nice unified, say, model that somehow unifies both possibility theory and Dempster-Scheffer theory. Okay, now I will briefly give some ideas of how this can be applied to a practical problem. I will take here an example of a simple problem of statistical prediction. Okay, we take a simple model, assume that X is the lifetime of a piece of equipment, supposed to have an exponential distribution with rate theta. And we observe an ID sample of lifetimes for n machines, and we want to predict the lifetime Y of a new piece of equipment. Okay, so here there's a general method. I don't have time to go into all the detail. I tried just to give some rough idea here. So that the general approach here, in this framework, is to express y as a function of the parameter theta and a pivotal random variable w with known distribution. And this can be done actually by considering the cumulative distribution function of y, which here is this exponential CDF. So it is well known that if you apply this CDF to the random variable y, you get a random variable w with standard uniform distribution. So that y, by inverting this equation, y can be written like this, that is to say, as a function of parameter theta and a random variable w with known standard uniform distribution. So in a way, you see that if theta is known, the only uncertainty is due to w, and this is aleatory uncertainty. In real life, theta is unknown. So let's say you have a combination of aleatory uncertainty and epistemic uncertainty, but theta is unknown, but it is constrained by the normalized likelihood function, which I remind you can be interpreted as a possibility distribution. And so here we express y as a function of two variables, w, which is constrained by a probability distribution, and theta, which is constrained by a possibility distribution. Okay, so here you see that actually here we can express theta as a function of y, and replacing theta here in this expression by its expression as a function of y, we get a possibility distribution of y for fixed w. And so if we fix w, here the idea is, if we fix w, the possibility distribution on theta, which is a fuzzy constraint on theta, gives us a fuzzy constraint on y. And this is for all w, okay? So now we have probabilities on w. So actually what we get here is a random fuzzy set, okay? This random fuzzy set here is continuous as opposed to the discrete models I've described before, but the underlying ideas are the same. Okay, from this random fuzzy set, we can derive a predictive plausibility measure and the predictive belief function using these equations, which are basically the one I described before. I remind you that the plausibility is the expected possibility, and the degree of belief is the expected necessity. Okay. So we get here a pair of predictive belief function and predictive plausibility function. In particular, we can define lower and upper predictive CDFs by these equations, and we can compute these functions and approximate these by Monte Carlo simulations. So here I show a small numerical example with a sample of size 10 of an exponential distribution. The rate here is taken equal to 1. So this is the empirical CDF. This is the relative likelihood, which we can see as a fuzzy set of likely values of the parameters after observing the data. Here I showed 10 fuzzy sets, y tilde, that's 10 conditional possibility distributions for 10 different values of w. From these, we can, by integrating over w, we can compute this predictive contour function, which gives us, for each value of y, the plausibility, its plausibility. So this is a predictive, what's called the predictive contour function. It gives us a plausibility of each individual value of y. And this is a plot of the lower and upper CDFs that I show here together. The broken line here is a plug-in CDF. Okay, this method has a number of properties, which unfortunately, because I'm running out of time, I don't have time to explain in detail, but there is some frequency calibration property. And from this pair of predictive, belief, and plausibility function, we can actually derive asymptotic confidence intervals on the true probability that Y belongs to any measurable subset A, or the real line. So first, I don't have time to really explain all the details here, but let us just note that there is some calibration property. And the second property is that it's compatible with Bayes inference, in the sense that if the possibility distribution represented by the relative likelihood is combined with the Bayesian prior by Dempster's rule, then the predictive belief function is actually a probability, and it is a Bayesian predictive probability distribution of Y. Okay, so we get back the Bayesian, let's say, analysis if we have a prior on the parameter. But the point here is that we don't need a prior. So this can be seen as a kind of Bayes inference without a prior. Okay, so I'm almost done. So to summarize this talk, I think this random fuzzy set model actually unifies quite a number of different models which are used extensively in computer science, artificial intelligence, and engineering. In particular, it encompasses possibility theory on the one hand and Dempster-Sheffer theory on the other hand. And I think this level of generalization, I think it's not generalizing just for the sake of generalizing. I think it's actually useful to describe different kinds of uncertain information that arise in engineering applications. And finally, a few concluding remarks. First, random fuzzy sets appear in the literature with different interpretations. This is not a new concept. I don't claim it's a new concept. For example, some authors use this model as a model of a random mechanism for generating fuzzy data. But here, our interpretation is completely different. It's purely epistemic. Also, in Dempster-Sheffer theory, a belief function is not interpreted as a lower envelope of a set of probability measures. So this, let's say, belief function model is not an imprecise probability model. Okay? And so here, what is, let's say, theory of imprecise probability is an alternative model or competing model, and it doesn't fit into this framework. And finally, propagating random sets or random fuzzy sets requires a combination of set propagation techniques, such as interval analysis, constraint optimization, and probabilistic techniques like Monte Carlo simulation. And I'm currently working in this direction of how to combine this set theoretic tools and probabilistic tools to propagate and reason with fuzzy random sets and random fuzzy sets. Okay, so these are a few references. So this first paper here is basically the paper that tells the story I told today. It will appear in Fuzzy Science Systems. And these are two other papers with a slightly different model, but that, let's say, go deeper into that statistical prediction, the application of random sets for statistical prediction. And these papers are available from my webpage, which is shown here. Okay, I'm done. Thank you for your attention, and I can take questions.
Thank you very much, Thierry, for your very interesting presentation. If anyone would like to unmute their microphone to ask any questions, please do so. Alternatively, if you write them in the chat, I'm happy to read them out too. Any questions?
Maybe I try. Thank you, Thierry, for a very interesting talk. It was really exciting and fantastic work. I'm just curious about your one of your latest remarks about imprecise probability in the previous slide, and he's saying that DS theory is kind of competing. Can you elaborate on that? I mean, it's an interesting.
Yeah, because
comment.
actually, okay, if you get a belief function, it gives you a set of compatible probabilities, which are basically the probabilities, all the probabilities that dominate the belief function, okay? So a belief function gives you a set of probabilities and actually is a lower envelope, okay, of a set of probabilities mathematically. But this interpretation actually is not correct because it's not compatible with Denoeux's rule, okay? And so in particular, if you condition, let's say you condition by some set, okay, from the imprecise probability perspective, you would consider all the set of all conditional probability distributions, okay? But the set of all conditional probability distribution obtained by conditioning one probability distribution in the set of compatible distributions, compatible with the belief function, that set of conditional probabilities is not the same, is not what you get when you condition the belief function by Denoeux's rule, okay? So for every model of uncertainty, there is kind of a static part and a dynamic part. The dynamic part tells you how, let's say, beliefs are updated, okay? So at first glance, it might seem that just looking at the static part, okay, a belief function could be interpreted as a lower probability, but the dynamic part of the model, which is for belief function theory, the Denoeux's rule, is not compatible with that interpretation.
Okay, so in the framework of updating beliefs and this within this conditioning rule, this probably doesn't apply anymore. Okay, thanks very much for the clarification.
We have another question in the chat too. Corrado Menka asks about the normalization used in the definition of fuzzy set combination. Technically, this might be convenient, but what about the semantics?
Yeah, it's I agree that this normalization step, which is not as well justified, I would say. This part is from possibility theory. It's not as well justified as a normalization in Denoeux's rule. I think I can explain very well the normalization in Denoeux's rule in terms of conditioning, okay, the joint probability. I must say that I agree that it's not so, I didn't yet find such a nice explanation for the normalization of the possibility distribution. And so this is something I would be interested, if you have some ideas, I would like to, this part is from possibility theory, okay? On the one hand, we need a normal, we need to get a normal fuzzy set. And okay, this normalization seems to be the most natural way to obtain a normal fuzzy set, okay? But I agree that the explanation is not so nice as the explanation of normalization Denoeux's rule. Okay, there's another question about the resemblance between the possibility distribution and likelihood. Yeah, I think this is a very interesting aspect. So coming back to that slide. Okay, in statistics, it has been known, of course, for a long time that a likelihood function, of course, it's not a probability. It's not a probability distribution. It's something else, okay? It's something that when combined with a prior gives you the posterior, okay? What it is, okay? But actually, some authors like Didier Dubois, Philippe Metz, and others have noticed that actually you can interpret this likelihood function as a possibility measure. So I would as a possibility distribution. You know that for instance, okay, if a value of the parameter is likely, okay, this is not evidence for the parameter, okay, because you may have actually many values of the parameter which are equally likely, okay. So what we have is that if some value of the parameter is not likely, okay, then this is evidence against the parameter, okay. So you have the similar interpretation as possibility, okay. Then you have some operations that we do with likelihood functions that are the same operation that we do with possibilities. For instance, take the profile likelihood. Right? When you have several parameters and you have, say, a parameter of interest and a nuisance parameter, we eliminate the nuisance parameter by taking the maximum or the supremum operation. And this is the same operation as marginalization in possibility theory, okay. Then take, for instance, the likelihood ratio statistics. It is basically the maximum. You take the supremum, let's say, or the maximum in the finite case, or the relative likelihood for over the null hypothesis, and it is exactly the possibility of the null hypothesis. So you see that they have this kind of convergence of things, which I think there is you can check also a paper of mine that appeared in the International Journal of Approximate Reasoning. I think it was in 2016 about this link between likelihood functions and consonant belief functions. The consonant belief function being the same thing as a plausibility function. I think it's an interesting point because it bridges two completely different fields of statistics and artificial intelligence, where this possibility theory was invented, let's say.
Thanks. I think there was one more question that someone wanted to say. I think we have time for one more.
Yes, that was me. Thank you for the very enlightening talk. I also have a question which kind of connects to the likelihood distributions, which is kind of similar but different. And it's about encoding confidence distributions in possibility distributions. That is like encoding the confidence intervals of some parameter in the alpha cuts of a possibility distribution. And I think that you mentioned this at the end of the talk, but unfortunately my internet skipped there, so I'm not sure if you actually said it. But I'd like to ask you what's your take on this, like encoding these confidence distributions therein, because I know that I heard secondhand that I think Lotvizade was not too much of a fan of this.
Yeah, it's true that if you take a nested family of confidence intervals, okay, and you can construct a possibility distribution like that, where so each alpha cut here of this possibility distribution will give us a confidence interval with a different confidence level, okay. But actually, if you take the relative likelihood, you also have this property for actually for a quite wide family of models. You also have this property. There's a theorem called Wills' theorem that tells you that actually the alpha cuts here of this relative likelihood are asymptotically confidence intervals, okay. So actually this likelihood function also has this property that it can be viewed as being built with nested confidence interval, except that here, except for some models, the confidence intervals are not exact. They are only asymptotic. And this is one comment. And the second comment is that what is nice with the likelihood function is that it's consistent with the Bayesian analysis, that if you combine it with the Bayesian prior by Demso's rule, you get the Bayesian posterior. Okay, so by taking this, by considering this particular possibility distribution derived from the likelihood, you keep you're still consistent with the Bayesian approach, I would say.
Okay, thank you very much.
Let's thank our speaker again, Thierry. Thank you very much again for your talk. And I'm just going to introduce our next speaker now. So Without further ado, Professor Michael Goldstein will be presenting the basic principles of reasoning about uncertainty, a subjectivist approach. Michael Goldstein is a statistician at the University of Durham, who has worked for many years on the foundations, methodology, and applications of Bayesian statistics. In particular, he has developed the general approach termed Bayes linear statistics, which is similar in spirit to conventional Bayes, but takes expectation rather than probability as the fundamental primitive for the theory. For the last 30 years, his main area of application for this theory has been to the problems of uncertainty quantification and decision-making for complex physical systems modeled by computer simulators. So I welcome Michael Goldstein to the floor. Thank you very much.
Fine. Okay. Where is it? Okay, so thank you very much. Very happy to be here at this interesting meeting. Of course, when you're talking about principles, really you should do it around in a pub, sitting around with a drink and reasoning and arguing. But let's see what we can do. Okay, so I want to give you my take on sort of how uncertainty, how subjectivism works and how uncertainty reasoning is done. Okay. So again, because uncertainty means many different things, let me tell you where I'm coming from. Okay, so I work, as my introduction just said, on large complex physical systems studied by mathematical models, implemented high-dimensional computer simulators. I expect many of you live in that world. Okay, so let's just give a few examples to see what we're talking about. For example, natural hazards, floods, volcanoes, etc. Climate change, what we think we know about that comes from looking at big computer models. Galaxy formation, how we think about the whole universe. We have models for the universe. Energy planning, we want to hit zero carbon, and while still actually having energy. There are big models that try and do that. Disease modeling, we're very conscious, that people, everything that all of the rules that people are trying to get us to live by are informed by big models. So these 5 are just there, not quite at random. These are just things that I have worked on quite a lot. So in each one of these areas, I have had grants, I've worked with postdocs, worked with scientists in the area, gone to conferences published in these areas. So I'm fairly confident in saying the following: the science in each of these applications is completely different, but the underlying methodology for handling uncertainty is the same. There is an uncertainty subject, and when I talk about uncertainty, I am thinking about pushing models like this into our uncertainty about the world. So therefore, when people cut uncertainty different ways, these are what I think are the sources of uncertainty. Firstly, a model will have a big input uncertainties. I mean, in order to run them, you need to specify the parameters under which the model works. There's all sorts of boundary conditions, initial conditions, forcing functions that you need to set up. You don't know what these are. The functions themselves are unknown. This is a hard thing to think about, but if I have a climate model, for example, a single evaluation takes days, weeks, months on a big computer. Really, you don't know what the function is, apart from where you've evaluated it. The stochastic uncertainty, think about a disease model. You have agents and they randomly interact. So there's an element of stochastic uncertainty. If you suppress that by running differential equations, you have uncertainty, you just haven't expressed it. You can't solve the model exactly, so you have solution uncertainty. Even if you could work out all of those top 5 exactly for your model, the model would still just be in a model, and you would have structural uncertainty relating the model to the physical system. You then match it to data, and data has measurement uncertainty, and so the data is always measured with error. You want to understand the system. We want to give advice about climate or about disease behavior. We have multi-model uncertainty. There are many models involved in this. And finally, we want to make decisions. The things we can do in the world and the things we can do in the model are not the same. So when I talk about uncertainty, we have all of these features. If you are working on an important model with important real-world consequences, you need to handle all of these things. So uncertainty is all of this, plus, of course, many more things. So a statistical analysis, for example, in climate research, results in a collection of uncertainty statements. So our first question is, what do these uncertainty statements mean? So here's a typical statement, okay? So there was a rapid climate change program. I mean, people are or should be worried about climate change happening rapidly. We can see around us that it is. And so the question, the comment is, fortunately, rapid climate change is an area in which the UK has taken the lead. The aim of the rapid climate change program is to determine the probability of rapid climate change occurring. So people reading that, I think, oh, I wonder what rapid climate change is. But me, as a statistician, I wonder, what does the probability of rapid climate change occurring mean? The probability. Do I understand what that means? Is it even worth me trying to understand it? Is this just a common language thing? But no, this thing is taken from, see, the rapid climate change was an ERC program that I was part of. It was a very interesting program. And so the rapid watch was a series of arrays. You drop things at the bottom of the ocean, you look at the ocean flow, and you try and understand the risk due to rapid change in the meridional overturning circulation, the MOC, which is an aspect of the Gulf Stream. Could the Gulf Stream basically slow? And there, right in the call, they talk about the probability of rapid change in the MOC. Okay, and they double up on that because the whole point of the project was to estimate the probability of rapid MOC change. So to estimate it, it has to be a thing. Okay, and so what is the probability of rapid change? Okay, do I know what that means? Does anybody on the project know what that means? We could make a whole discussion for 45 minutes on, do we understand what that means? Okay. But they double up on that further when they say the aim of the project, and as a statistician on the project, I have to do this, is to make sound statistical inferences about the real climate system. Now, of course, I would go around making talks and I would make the joke, why do they even say this? Because obviously we don't want to make unsound statistical inferences about the fake climate system. So obviously we want to do this, but what does that mean? What are sound statistical inferences about the real climate system? And how would we do this? Okay? And all I can say is that the Rapid Watch program was a serious scientific program, involved serious scientists doing much good work. We certainly did not answer the question, what does it mean to make sound statistical inferences about the real climate system? I don't think anybody knew what that would mean. This is not a jab at Rapid Watch. It's not a jab at climate science. Okay, so I would say that most areas of application are based on large modeling activities linked to complex data sets. So what we mean by uncertainty is crucial to understand what our model tells us about the real physical system. And really, we do not understand what our words mean. Okay, I mean, it's not a slam. It's just that if I asked you what you actually mean by it, to the extent that we are going to tell everybody in the world to change their behavior in order to control climate or to control, disease spread, what are the statements that we're making? What is their meaning? And so what does it mean to make sound statistical inferences about the real climate system? So let me go back. This isn't a new question. So Jimmy Savage, I mean, when he wrote his book in '54 on the foundations of statistics, said, here's a quote, it's a good quote. It is often argued academically that no science can be more secure than its foundations. If there's controversy about the foundations, there must be even greater controversy about the higher parts of the science. So he's being a bit ironic here because he says, his implication is that in fact that we ignore the controversy about the foundations. He goes on to say this: it's unanimously agreed that statistics depend somehow on probability, but as to what probability is and how it's connected with statistics, there has seldom been such complete disagreement and breakdown of communication since the Tower of Babel. So that was in 1954. Okay, so has it changed? Have we now basically sorted this out? Do we agree? Interesting question. I would say not. And my talk is exploring this. So let's talk about the real world meaning of an uncertainty statement. So A is an event like rapid climate change. Let's suppose that we can agree what that would mean. And so the probability could refer to a probability property of the world. So in this view, there are true probabilities, and our aim is to make true probability statements about these true probabilities. So I want to know the true probability of rapid climate change. So I will make uncertainty statements about that. So can we give a meaning to these things? Okay. So I want to sort of step back a bit and talk about the relationship between different types of uncertainty. Okay. So let's go back to the general notion that people carry about epistemic and aleatory uncertainty. So in many contexts, uncertainty is considered to be of two basic types. Our previous talk sort of referred to this. There's epistemic uncertainty is our lack of knowledge. We could reduce this by receipt of further information. And there's aleatory uncertainty, which we usually call basic intrinsic chance variation, which can't be resolved. So the distinction is informal rather than precise. So many of our models have aleatory uncertainties. For example, I mean, the previous speaker gave an example of somebody having COVID, or will they get COVID, will they be infected, etc. You could imagine that that's set up as an aleatory probability, but as we get more information, we say, aha, we know this person is a man, he has the following lifestyle. Gradually, as we resolve this, we remove some of our aleatory uncertainty into epistemic form. In deep science, you know, we will make deep insights which will transfer these things. So, okay, so, but we still have these two concepts, okay? So in a Bayesian analysis, which I expect all of you at least have seen examples of, so aleatory uncertainty is the likelihood. We have the likelihood of data given population parameters. Epistemic uncertainty is the prior distribution over the parameters. For example, we have a Poisson sampling. Okay. The Poisson distribution will be the aleatory part. We're looking at a radioactive substance that's emitting particles. So we have an aleatory uncertainty through that. Our epistemic uncertainty is that we do not know the rate. So this raises fundamental questions when we seek to apply the results of the model to actual real-world inferences. For example, we do want to go into lockdown for COVID. We want people to completely change their behavior. So we have a model in which these things live. How do we translate that into statements which people should be prepared to change their entire way of life based on? Okay, because what we observe are individual measurements of things. We see Dave gets COVID. We see Judy appears not to get COVID. So we create models and we need to justify these things. Okay? So what I'm now going to talk about, so the first part of my talk is effectively in harmonizing all these things through a subjectivist view. And the second part will be to step back and say, well, how does this subjectivist thing work? Okay, so we're going to show about how we construct parametric statistical models based on uncertainty statements that we make, which are defendable, and we make about observable random quantities. So this will be based on the key idea of exchangeability that I'm going to build up to. Okay. So let's start with finite population sampling, because let's start with an easy example which we can understand, which is very concrete. And then once we understand the concrete example, we can then move back and then apply it to things which are much less clear. So I'm going to talk a little bit about finite population sampling to make sure we understand that and we all agree. And then we'll push that into areas where it's less clear. So let's start. I mean, our previous speaker talked about an urn. I like to talk about a bucket. So a bucket has a large number big N of counters, and we know what big N is. An unknown proportion of these Q are red, and the remaining 1 minus Q are blue. So it's a very straightforward, very physical setup. So we're going to draw a counter at random from the bucket. So that just means all the picks are in some sense equally likely. So I'm going to draw one counter from the thing. I create a random quantity Z, which is going to be 1 if I draw red and 0 otherwise. So we're uncertain as to what the value of Z is going to be. And this uncertainty has two components. Firstly, we don't know the proportion of red counters in the bucket. That's epistemic uncertainty. I could reduce that uncertainty by somebody could tell me, or I could just get information about that. Different people will know different amounts about Q, so their epistemic uncertainty may differ. If we did know Q, we still wouldn't know what the value of Z was, because there would still be a randomness. That would be the realization of a Bernoulli random variable parameter Q. So in my story, that's irreducible, and the second part's aleatory. So let's now look at this a bit further. The possible values of Q are Qi's, which is I over n. It could be naught, it could be 1 over n, 2 over n, etc. Okay. So our epistemic uncertainty for Q will specify our collection of probabilities, our probability for each different value for Q. So our probability that we draw a red ball, or red counter rather, is given by the law of total probability. The probability that Z equals 1 is the probability Z equals 1 given each possible proportion of red counters times the probability of that proportion. If Q equals Qi, the chance of getting a 1 is just Qi. So the probability Z equals 1 is given by that sum. Now I'm building up to a theorem, so it will be handy for me to rewrite this. So I'm going to write this as the integral of Q with respect to a probability measure. That probability measure is just going to assign probabilities Pi to the points I over n, but it's just a nice alternative way of writing it. So now I'm going to take a sample not just of 1, but of a size little n without replacement. So I'm going to take a sample of size 5, say, and I'm going to count the number of red counters in my sample. So epistemic uncertainty is as before. I still don't know the proportion of red counters in the bucket. Aleatory uncertainty is the probability distribution of X, the number of red counters in my sample of 5, if I know the proportion of red counters. So that's a hypergeometric distribution. So the chance of getting 5 red counters is on the top, the number of ways that I could choose. Well, the chance of getting 3 red counters from a sample of 5, I have to choose 3 from all of the red counters and 2 from all of the blue counters. And I multiply those for the number of ways I can choose 3 red and 2 blue, divide by the total choices of 5. Okay. So the probability distribution for X, the numbers, so what's my chance of getting exactly, say, 3 red counters, is just my integral of my hypergeometric over my distribution for Q. So if I imagine big N is very big, and I'm choosing like 5 counters from, say, a bucket full of, say, 1 million, then basically I've got binomial sampling. So my probabilities for 3 red counters out of 5 is a binomial sample, and approximately I can write this down. Okay, so when I write down binomial sampling, this is what I basically have in mind. So often I use that to say that X has a binomial likelihood, parameters N, the number of trials, and Q, our probability of success on each trial. And I don't know what Q is, so I have a prior measure for that, and that's given by F. So now, in this case, sampling from a bucket, basically everybody's going to agree. Okay, I mean, this is why we start here, and that's why we start by teaching our students this. If we take a proportion of red counters in the sample and we take a large sample, basically we'll find out within an error that we can describe what Q is. So the point about this is that the meaning is clear. There is a true but unknown population parameter Q, which is in principle observable. I can look in the bucket, and there's a widely agreed aleatory description as to how the sample is drawn given Q. Okay. So in the bucket, everything is clear. Now, most statistical problems lack this logical bedrock. Okay. If I think about COVID, okay, it's not like that at all. Okay. So I was thinking firstly to set up an example where we have COVID and certain people may or may not, but that was so depressing. So let's imagine a simpler version, which is still unclear. The simplest version I can have, instead of having a bucket, I'm going to spin a coin. Okay, so I spin a coin, say 5 times, I see how many times there are heads, and I want to make an inference about future spins. It's like COVID, but not horrible. Okay, so how could we do this? We could set up a true but unknown value Q of the probability that the spun coin will land heads, and then I could say the coin spins are independent Bernoulli variables with parameter Q. If I did that, what I've set up now is exactly the same probabilistically as my bucket. However, there's a big distinction here. In the bucket, it was clear what Q was. When I talk about spinning the coin, there is no real world quantity Q. Okay, even in principle, there is no real world definition. If you push me on this, I could not say what Q was. I could not give a definition for it. Okay, and even in principle. When I think about COVID, I mean, for the coin, it doesn't really matter. When I think about COVID, if you push me on this, every time I see an announcement, but from SpyM or whatever, and I say, if someone asks me what exactly are they talking about, really, there is no exact statement of what these things mean. And again, it would be interesting, you could try and open this up. Really, there isn't. So what is the bridge between the uncertain models? Okay, and so what I'm now going to do is I'm going to create the bridge between uncertain models and finite population sampling. That comes through the idea of exchangeability. Okay, so now let's get back to the bucket. Okay, so now I'm going to draw the counters one at a time. X1 is the first, X2 is the second, X3 is the third. Okay, and each Xi is going to be 1 if the I straw is red. And then I'm going to take a subsample of those. So instead of drawing all the big N, I'm going to take a subsample, maybe the 3rd, the 5th, and the 19th. Okay. Now, what does that probability distribution depend on? It only depends on the number in my sample, not the choice of indices. So if I look at the 1st, the 2nd, and the 3rd, or the 7th, the 19th, and the 4th, they will be exactly the same. I'm sampling from the bucket. There's no difference between these. Okay. And what we say here is that the probability distribution of any collection of little n of the quantities depends only on the value of little n, not on the quantities selected or the order in which they're arranged. My 1st, my 2nd, and my 3rd together, my 5th, my 17th, and my 19th, my 4th, my 23rd, and my 18th. All of these, they're just samples of 3. They will have the same distribution. A set of random quantities which have that property are termed exchangeable. So the concept of exchangeability is general. I mean, even though I seem to be talking about two valued things. So you could imagine that I'm sampling individuals. I sample Dave, Fred, Julie, Bobum. I sample a series of individuals, 1, 2, 3, 4, 5, 6. For each one of them, I write down a big set of details about their symptoms. To say they're exchangeable means that any, say, collection of 4 of them, I would have the same probability distribution for. Okay, so you can see that often I will make this judgment of exchangeability. It's a natural statement to make about my state of knowledge about a sequence of random quantities. Okay, so in the account from the bucket, I told you about my physical model and I deduced exchangeability. But what I'm now going to do is to reverse the logic. I'm now going to get somewhere. I'm going to say, supposing I start with exchangeability. So my comment is that exchangeability is a judgment that I can make. It's a real world judgment. Often I make this judgment. And what I'm going to do from exchangeability is that I'm going to now deduce the structure of the problem directly from my judgment of exchangeability. So I have a group of individuals, okay, and they have a certain COVID status. And supposing I simply judge them to be exchangeable, that's a statement that I make and which I can explain what that means. So now let's come back to spinning the coin. So I'm going to turn this coin into a bucket. So I'm going to spin the coin repeatedly. So let ui equals 1 if the I spin is head, ui equals 0 otherwise. Okay, so I now do my coin spins. So let's suppose I view my coin spins as an exchangeable sequence, which I do, in fact. Okay, that's defendable, and it does correspond to what I think. So I'm now going to turn the coin into a bucket. Consider the following thought experiment. So I have an empty bucket and I have a pile of counters numbered 1 to big N. So I'm going to imagine, I'm not going to do this, I'm just going to imagine spinning the coin n times. On the ice spin, I pick up the ice counter and I mark it either 1 or 0, and I add that counter to the bucket. Okay, so the bucket is going to have n counters in. Each counter will have a 1 or a 0 in, depending on what happened on the ice spin of the coin. So now imagine I make the following thought experiment. I can spin the coin once and observe whether it's heads, or I can spin the coin n times, fill my bucket, and pick out one counter from that and see whether that has a 1 or a 0. Each one of those, because of exchangeability, must have the same probability Q of seeing a 1, okay? Because my first spin is exchangeable with all my other spins, so I just now basically used that exchangeability, okay? So as a key point, I mean, is that I can imagine creating a series of big N spins, physically creating them in the bucket, picking one of them out, or I can just spin it once. Okay, so the probability for the random selected counter in the thought experiment, okay, is I can now consider the possible values for the proportion of counters. I can assign probabilities, okay, as follows. Okay, so basically my probability that my first spin is 1, okay, is I can just now I can look at all the possible proportions Q that there could be for the number of counters in the bucket, and then I can integrate over those proportions. So I've now got my first spin, and I've now created it by a statement that is just like my statement in the in my finite population sampling. So I can now imagine doing n tosses in the same way. So I'm going to spin the coin, say 5 times. So my probability of seeing 3 heads in 5 spins must be the same as I create my big N bucket, and I draw K counters labeled the 1, okay, in there. So my probability of seeing 3 spins in 5 tosses is my integral of my hypergeometric, okay? So let's look at this quantity here. So this is true for any value big N. I could, if I'm doing 5 spins, I could create a bucket with 20 and then pick 5. I could create a bucket with 100 and then pick 5. I could create 1,000,000 and then pick 5. All of them will give me my same probability for 3 heads out of 5. So I can let big N go to infinity. As I let big N go to infinity, the hypergeometric goes to the uniform. And this is a bit of math I need to do. My big Fn statement tends uniformly to a limiting distribution. So my probability of 3 heads in 5 spins must be exactly equal to the following statement here. It's a binomial for given Q times integrated with respect to a distribution over Q. And that I just shown you is De Finetti's representation theorem for an infinite exchangeable sequence of binary outcomes. If I have a series of coin spins or a series of people who have COVID or don't have COVID, effectively I must act as if I consider there is a true but unknown value of Q, and from which I have a binomial sample. There's my aleatory part, and I must have a probability distribution F over Q, okay? And I've done it for coins, but I'm running out on time probing. So the following statement simply says that I could do this for any set of random vectors. And I've written down here the very famous Stewart and Savage theorem that says an exchangeable sequence, which is just a set of judgments, effectively means that I can create, I must create an aleatory description of Q and an epistemic distribution F. And so I'm running out, I'm going to skip statements here, but I'm just going to make a general point here that relative frequency definitions are funny because what is relative frequencies? Why do they converge? And etc. Okay, then a judgment of exchangeability, which is a natural thing for me to make, it's a natural thing for me to explain, okay, leads me in a subjectivist way to create a representation which has what is so-called aleatory and epistemic points. So the point being, therefore, that to me, yes, the division is natural, but it doesn't mean that I stepped outside the subjectivist world. The subjectivist world is strong because in the subjectivist world, you can be very precise about what everything means. I can tell you very exactly what my judgments were and how they lead to these things. Okay, so now, now moving on. So in the subjectivist view, the meaning of a probability statement is straightforward. It's the uncertainty stat judgment of an individual, okay? So instead of the probability of rapid climate change, we have Ann's or Bob's statement, and we've seen that that can have powerful consequences. So what are we trying to do in the subjectivist Bayes analysis? We want a methodology to support when Anne and Bob reaches these probability statements, their judgments are transparent and they're reasonable, and their judgments can be critically assessed. Okay, and different experts may reach different judgments, and that's part of the analysis. So when I talk about subjective Bayes, I tend to talk about 3 levels. Firstly, there's an individual who's thinking very hard. That's a subjective Bayes analysis. Then there's an analysis of the range of judgments that it would be reasonable to hold given the differing views of experts. That's a scientific Bayes analysis. Science isn't what you think, it's what what science leads you to. And then you may get to a point where if a scientific question is answered, and that's because the analysis is sufficiently clear and compelling that all agree, and experts would agree. And that's what I tend to call an objective Bayes analysis. And let me quickly put up a statement here. What do we mean by objective? Why am I using that word? Here's a statement from the Internet Encyclopedia of Philosophy. An objective judgment or belief is a judgment based on objectively strong evidence, which will be compelling for any rational being. A subjective judgment is a judgment that's compelling for some beings, but not compelling for others. And I make the comment that that's why objective judgments, that's the gold standard, and subjective Bayes effectively has an aim for that, but not a requirement. Okay, so now, now I see my time running, but let's keep going on this. Having said this, now I've been very strict about talking about meaning. Let's say that it is a fact that it is actually very rare to see a Bayes analysis which claims to be any of those 3 things that I just put up. Okay, so I've been a Bayesian statistician for many, many years. I've worked in many, many, many areas. I've very rarely seen a serious Bayes analysis of a serious problem, and they said, and that is my judgments. Okay, and now that raises basic questions. If meaning comes from the meaning of Bayes, and so I'm now going to discuss the problems in bringing Bayes to reality. And even though I'm talking about Bayes, other uncertainty analyses have all these problems and more. So let's now finally write up Bayes' theorem. So what are the problems in actually doing this in complicated problems? Okay, firstly, just actually specifying all these quantities on the right-hand side is a huge task. Think about all the uncertainties involved in bringing uncertainty about climate to bear. Okay, then the calculations are hugely complicated. They're MCMCs on very complicated things, which are fragile. They're poorly done. It's very insensitive. Okay, so all of that is very complicated. And then, but let's imagine we've fixed all these things. Supposing we could specify all the quantities on the right-hand side exactly. It's a simple problem. What does the probability of B given D actually mean? Okay. Now I realize I've opened a big box without giving myself a big amount of time, but I need to hit this because it's very important that you might think that someone somewhere has proved that conditioning is the correct way to modify beliefs in some worlds. But in fact, if you look at foundations carefully, okay, what foundations argues is the following. Here's me, I specified a joint distribution for a collection of random quantities. I've written down a rule for changing my probabilities for some of the quantities as a function of the rule values for the remaining quantities. So Bayes' theorem is an example for that. I've told you about my conditional probabilities of D given B, and then I've written down a rule for changing them. So the statement is, if my rule for changing my probabilities is not the usual conditional probability formula, then I can be made a sure loser. Okay. Now, that does not mean that beliefs should change my conditioning. It simply means that if I write down now a non-Bayesian rule for updating beliefs, then I'm going to hit problems. So let me now ask the fundamental question of inference. What relevance do conditional probabilities hold for actual posterior probabilities when I do learn the event outcomes? So now I write down my P of B given D, and etc. By the time I observe the data, I may have come across unanticipated or relevant information. I've gained further insights about the problem. This doesn't correspond to Bayes conditioning. Okay. So I've never seen a non-trivial Bayesian analysis which actually proceeded according to the usual Bayes formalism. People write down a Bayesian model, they get the data, they do loads of diagnostics, they retrofit it, they do all sorts of things. This isn't a hypothetical. Okay, people don't do Bayes conditioning and that's the answer. They never do. And even as a point of logic, they're not wrong to do all this. So if I made the learning of the outcome, I mean, supposing I just learned the outcome and nothing else, okay, then I've learned nothing else. That's actually a statement of fact. If I was in a trial and evidence was presented and with no other evidence was presented, that would be part of my learning. It would not be part of my conditioning event. So there's nothing in the conditioning arguments which says that my actual posterior judgments should be my conditional judgments. It's really not part of the argument at all. So now if you go back to the foundations, okay, then in the earlier version writings, this is kind of recognized. We talk about what perfectly rational individuals might do, not us, perfectly rational individuals. We talk about small worlds and etc. So Bayes analysis effectively is a model for inferential reasoning. It's not the answer to what inferential reasoning should be. So just as climate scientists study climate by means of climate models, Bayesian statisticians study uncertainty judgments by means of Bayesian models. So climate models are a crucial source of information for studying climate. But if you thought the climate models were the same as climate, you would be making a mistake. Our Bayesian models are informative for our actual inferences, but they're not the same as our actual inferences. So let me quickly, I'm running out of time, I can see that. But when you think about a model tells you how system properties affect system behavior, but you approximate system properties, you approximate the rules for finding system behavior given system properties. That's why the model is useful, because the real world is just too complicated. So Bayes analysis does the same thing. It simplifies system properties, it simplifies the rules, okay? So now, let me quickly give you my view as to what Bayes is a model. Why is it a good model? So here we have two events A and B, the simplest version. I make current judgments about P of A, P of B, and P of A given B. I'm going to observe B, and I'm going to update my probability for A. So the question is, what does P of A given B tell me about my revised probability for P of A? So I'm unsure about what my inferences are going to be, just what will occur to me and everything. So I ask, what, if anything, is the relationship between these quantities here and my probability at time t for A? So I need some notion of temporal rationality that's going to tie these things together. So current beliefs cannot constrain future beliefs. Anything I believe now, I could get better beliefs in the future. So the thing to understand is that current beliefs can't constrain future beliefs, but future beliefs can constrain current beliefs. Okay. If I knew what I was going to think in the future, and I knew that what I thought was thoughtful, that should have an inference about what I think now. Okay. So I'm going to now jump into, it's like the key statement that I think you always need to think about when you're using Bayes as a model, what I call temporal shore preference. How can future beliefs constrain current beliefs when I don't know what my future beliefs are? You think, well, do I have to get into a time machine and come back into the past and say, well, in the future, I'm going to think this? Clearly not. But let me set this up. I have two random penalties, J and K. At some time in the future, these are going to be revealed and I'll pay the penalty I've chosen. So what I introduce is the notion of a Shore preference for J over K at future time T. Supposing I know now that in the future, I will not prefer K to J. I know a point of logic, okay? So then the temporal short preference means that if I know that in the future, I'm not going to prefer a K to J, then I should prefer J to K now. Okay, yeah, okay. So suppose I have a short preference for J over K at future time T, then my current belief should respect that. So when you first look at that, you think, well, that's a bit funny. how could I have a short preference in the future? How could I know I was going to have a short preference? So the temporal short preference principle doesn't say that I do have any. If you go through your whole life never having a temporal short preference in your life, then you obey the temporal short preference principle. All I'm saying is that if you do have a temporal short preference, then you, in the future, you should respect it now. And the funny thing about temporal short preference is that in fact, you do have millions of temporal short preferences, and they are what determine your attitude to inference. So let's now very quickly say, okay, that what is the implication of that? Supposing I just tell you that I obey temporal short preference, okay? I just tell you that anything in the future I will respect now. Then effectively, let me just quickly write this up because I know I'm running out of time. What it means is that I must now think that my conditional probability, I'm going to see B before I make my judgment, and then I'm going to update A. Then P of A given B is never going to, I'm not saying that it equals my posterior probability. I'm saying that the difference between my posterior probability, my actual judgment, and my conditional probability is a quantity, and that quantity has to be independent of the partition. Okay, that quantity R that I have, the difference between these two, has to have mean 0 and conditional probable expectation 0, given if B happens or if B doesn't happen. Okay, so temporal short preference doesn't make the impossible happen, that conditional probability equals posterior probability, though I have never a reason to think that, but it does tell me probabilistically how these things relate to each other. And I've done it for a single outcome, but it works for partitions and more generally. So if I think about mathematical models for physical systems, a climate model does not tell me what climate should be. It resolves some of my uncertainty about climate. And if I've done this carefully, as I should do, then I will say that my beliefs about climate are what my climate model suggested, plus some kind of error, and that error will be in some sense an add-on whose properties I will tell you about. So when I go from, say, a COVID model to real world, I should explain what my COVID model tells me about the real world. Typically I won't, or epidemiologists don't, and that's a problem with what they do. If they did, then they would have a principled statement like this. Okay. So now, what I've now done is I've told you that there is a principle which obviously you would need to look at, stare at, and then agree with, but I think I could convince you of, that would explain why the Bayesian model does relate to the posterior. It's not the same as, but it has a well-defined relation. Now, let me now say something, okay, that I wrote down 3 reasons why I would have problems carrying out the Bayes paradigm. One of them was that, in fact, it was just too complicated to do because probabilities are too hard to specify. One of them was the calculations were too hard to do. And the final one was, what is the relationship? I've done number 3. Let me quickly say, you know, even though I'm a Bayesian, I do not specify probabilities. It's too hard. I use expectation as a primitive simply because, there we go, expectation is a much better primitive to work with. If I work with probability, I have to specify such a level of detail that I just can't do it. If I work with expectations as a primitive, I can just pick the expectations that I need. Dave Finetti, in his book Theory of Probability, in fact, is a fundamental book on foundations, is really a theory of expectation for exactly that reasoning. So I use the Bayes linear approach, okay? And let me give a reference to that if you were interested. There's a book, okay, which goes into that in great detail. And I'm just going to say now that if I think about expectations rather than probabilities, I have, instead of using Bayes' theorem, I have rules for updating my expectations and my variances, which, again, I'm just going to point out that there are such things, okay? And I'm going to tell you that if I do this updating, basically, if I wanted to use my partitions and my Bayes theorems, it's exactly the same, that my adjusted expectation, if I specify a partition and probabilities over it, then adjusted expectation is simply that. But basically allows me, it generalizes my ability to condition on indicator functions. Conditioning on indicator functions, I think, means that the whole is fine as a model, but once I want to push this towards real statements about real things, it is just too hard. Okay, and so my final statement here, okay, I know I'm doing this hugely quickly, is that if I want to learn about some random quantities B in full generality, I am going to, at time t, I'm going to revise my judgments. Then my expectation will, in the future, will have a relationship to the real outcomes B. That's why I actually go through the process. My adjusted expectation, which is my generalization of conditioning, will have a well-defined relation to my posterior beliefs. They won't be the same. It will be an expression for this that will reduce my uncertainty. And therefore, I have a series of equations that basically describes, when someone says, when I created my model, my Bayes model or my adjusted expectation model, and I say, what does that say about my real judgments about real things? I have a precise answer for this. So what I said is, in principle, and if you're interested, you can follow this up, is that Bayes linear statistics is not how you should reason about the real world. It's a model for real world reasoning. So just as aleatory uncertainty isn't a thing, but exchangeability judgments allows me to explain exactly how I was using that thing to make a statement about my uncertainty about the world. Temporal short preference is my second principle that allows me to link reasoning about uncertainty to the thing, to the real inferences. So I have now very, very quickly covered many things. So let me highlight what I meant. Firstly, the meaning of uncertainty statements in current practice is unclear. When I see a statement about COVID, it hurts my heart that I do not know what people mean, even though, and I know that nobody, I see in many rooms with epidemiologists, they work so hard, they do such good science. What do they actually mean by their statements? I don't know what they mean. If you push them, they don't know. The implications for real world action are almost always unclear. Okay, so there are huge consequences of this. Okay, so uncertainty statements interpreted as a judgment of named individuals are in principle clear and useful, provided the individuals are expert and give sufficient level of explanation. I would be so happy to see uncertainty statements signed off by individuals. I never see this. Exchangeability is the formal and rigorous bridge between such assessments and most common notions of aleatory uncertainty. Most formal methods, like Bayes for quantifying uncertainty, you should think of them as models for the task of quantifying uncertainty. So you achieve 1 to 4 as a serious subjective judgment. Formal methods are models for these things. Temporal short preference is a powerful tool for taking inferences from models to real-world judgments. Choosing expectation rather than probability as a primitive, it makes all these things possible and it reveals a general structure. And finally, what do we mean by the foundations of inference? The foundations of inference, yes, it is about models for reasoning, but to me, the fundamental part of the foundations of inference are the study of the relationship between models for inference and actual real-world inferences. So at that point, to me, you've actually made a foundational sort of statement. So anything that I do, I mean, it's a model, and then it is what do I need to believe about the world in order for that model to make a statement about my uncertainty, and what is that uncertain statement? So if you were interested in any of this, let me give you some references. At the top, there's one about why you should be a Bayesian. Now, there's masses of, the first part, when I told you about the theorem, there's masses of great literature on this, and it opens up a whole way of seeing like statistical modeling. Here's my version of that, which links out to many other sort of good, proper references. For temporal short preference and etc., there's a general statement that I made. The next one, revising exchangeable beliefs, links up effectively exchangeability with temporal short preference. There's a couple of classics that I listed here about subjectivism. You know, many people have written many fine things. Had I thought about the person at first talk, yes, all of these things can be done in the context of implausibility, of imprecise, of lower provision, and etc. And provision is a great tool for this because effectively it allows you to look at more complicated things. I noticed that Matthias Troffes is was one of the people who's observing this, and he's written some very interesting papers allowing you to take these things and push them into the kind of sort of imprecise areas that Thierry was talking about. And finally, I put a few references down if you're interested in how these things transfer like to huge, like real problems. So there's one just on how you think about uncertainty for like the whole universe, if you're just interesting because it's a whole universe. There's one on Bayes linear emulation because it puts the Bayes linear sort of tasks in the mind, and it starts getting you to think about a bit more about how models relate to the real world. And finally, there's one on probably my best statement, again, with all these with collaborators who did vast amounts of this, okay, is on how generally we should think about how models in general and how our analysis of these things relates to our understanding of physical systems. So again, that's a series of thoughts that manages basically to look at temporal short preference without ever using the word and relates that to everything. So if you find any of those useful, you can contact me and I'm happy to give you the references or follow these things up. Let's flip back to that page because it's more what I talked about. Okay, so I know I touched on many things very quickly, but okay, now I'm done. Okay.
All right, thank you very much, Michael, and thank you for just providing so much rich information and going through so much in such a short space of time. A lot of food for thought and extremely relevant with all kind of these real world examples of COVID and climate change. I think we have a lot to think about. So does anyone have any questions for the professor?
Yeah, actually, I have a question for Michael. You use the expression actual real world reasoning. What do you mean by that? Is it are you referring to the way people actually reason in real life?
Yes, I actually, by actual real world reasoning, I mean you actually reasoning about the real world. So when I say, you know, at the end, my probability that you have COVID is 0.3, what I mean is not I did a model of that and that model came out with a number 0.3, so I'm just going to use it. I mean that I used my best attempts to assess what my personal real judgment is. Okay, and then I tell you how I did that. I tell you how I use models to support doing that. Yeah. So actual real world reasoning actually, it just means what they say. And it's funny because I sit, for example, in COVID workshop rooms, okay, with people who are expert, and I talk about, you know, what your actual judgment, you know, what the meaning of this is. And people find that hard even to understand what I could mean by asking what the meaning is. You know, they just do a thing and they create numbers and then they give these are the answers, and these answers are then given to determine policy. And if I say, well, you know, these things seem to have probabilities in them, what are these probabilities? You know, I don't understand. You know, I genuinely don't understand. You know, is this are you claiming this is a property of the world? And clearly not. Because if, I mean, the thing about, the bucket has a certain number of counters in it, okay? And that's actually a number. I might realize that I'm not picking them out in a very fair way, but there isn't, you know, I could open the bucket and there were counters in it, okay? But the probabilities, you know, in a COVID model, you know, somebody else is going to completely change, you know, what they're there, you know, the COVID model. And so these probabilities, it's not that you're, you know, I realized that my sampling was different. I realized these things just no longer even exist. And so they are not properties of the world. So if you ask, what are they? Are they entirely properties of your model? If they're entirely properties of your model, why should we change our entire life on the basis of them? And they say, oh no, they're much more than that. And then you say, well, what are they? So you need to understand effectively, you know, effectively people are telling me about their exchangeability judgments. And and when they talk about taking this model and changing it to that model, they're talking about a refinement about their exchangeability judgments. They are talking about extra ingredients. They are they are talking about partial exchangeabilities. They are talking about sort of different inference, real world information that they're putting in, and but they haven't got the language to talk about that. So therefore they don't do it. Anyway, I don't know if that answers your question.
Yeah, more or less. But I'm wondering.
I mean, by actual real world reasoning, the actual reasoning you actually do about the real world, however you choose to do it.
Yeah, but I mean, this actual reasoning good? I mean,
well,
I mean,
is it good or is it bad? Yes. And so this is why we have models. And so the models, okay, guide us in doing this. Yeah. So can I say, so when I say, can I justify doing this? Okay, then I can, I mean, if I want to talk about climate uncertainty, for example, okay, I can point to, part of my reasoning for that will be a very careful climate model that I've built. Yeah. And we can look at it, and we can look at it very carefully. We can look at the data, etc. Yeah. So when I talk about, in fact, the need to explain, what is the basis of my reasoning, yeah, okay, then showing you this climate model will be an important part of it. But showing you the climate model, I mean, a part of it won't be, here's my climate model, and I'm now going to make the statement that my climate model is exactly what will happen in climate. Yeah, because then I've gone from something that was helpful and constructive to something that is false, and which allows anybody who wants to deny what I said to say, yeah, but that's not right. Look, it's not exactly right. Here's all the reasons why it's an approximation. So I need to therefore to understand to what sense all of these things, the tools that we use, support our reasoning, and what sense there is still uncertainty. Yeah.
okay.
So when you ask good, then I could come back to you and say, well, what's the alternative? The alternative is to stay entirely within the model and not actually think about maybe how they differ.
No, but the point I was trying to make is, okay, if you take, for example, modeling, I don't know, the physical processes in climate change. Okay, there is something that exists in physical world, and trying to build model of it. If you say you're modeling uncertain reasoning, it's not so obvious that it's something that exists.
Okay, no, that's a fundamental. Yeah, I know.
The models. It's more like a guide, maybe without any notion of probability. For example, there's not even any such thing that a degree of belief person.
Okay, so this raises the fact there are two fundamental issues. Firstly, I mean, it's interesting in the climate model whether climate does exist. If you talk to climate scientists, whether that's just an artifact of their model. And secondly, okay, so whether probability exists or not, okay, I mean, given when people make probability statements, okay, it's up to them to explain what they mean by those probability statements. Now, I'm not saying that they have to mean what I meant by that. I'm happy for them to give another meaning, but they actually have to give that meaning. Yeah, it's not enough to say, some kind of, or rather, you can talk about it as something that exists in a model, and that's fine. And as modeling constructs, these are powerful and useful. But it's when they snap this thing out of the model and then they transfer it to the world, and they talk about the probability of rapid climate change, yeah, or the probability that you will get COVID, therefore we need to do something, that they need to give a meaning to that. Yeah, and so the reason I talk about the subjectivist views is that I can say what I mean by it, and I can say why all of these models and everything I did relates to that and enhances it. So if an expert says, I mean by this is my judgment, and I've used all of these great tools to mean that my judgment is really carefully worked out, then that's cool because I know what they mean. Yeah, I'm very happy for somebody else to mean something different, as long as they say what it is that they mean. And that's a bit that's always lacking.
Michael, I appreciate that. And I think you're absolutely right. There is a lot of protestations about uncertainty where people don't understand at all what they're even implying. But I was wondering, I want to preface by saying that as a resident of Florida, who has been transplanted to Liverpool, I can assure you that climate does exist.
No, weather exists. Every day you experience things. Yeah?
but I have a question actually about, because you sort of took pains to distinguish between the case with the counters in the bucket from the coin flipping, coin spinning. And I find this peculiar because it's as if you're trying to, well, you're saying that the probability of a heads doesn't exist in some sense, right? In a definite sense of not existing. But I don't understand why you need to go there, because clearly you would agree, wouldn't you, that if we made a machine whose job it was to spin a coin and it was giving, some answers, and some of them were heads and some of them were tails, and we could run that machine as long as we wanted, I assume you would agree that in that case, there's a physical reality to the probability of a head of that coin in that machine. You would say that, right?
No, what I would agree is that you could the coin. There's an in principle observable statement that I could spin the machine could spin the coin, say 200 times, and I could put the proportion in there. Yeah. Now, the concept of letting that number go off to infinity, and why there should be a limit to that. And in fact, see, it's hard to make this argument because, of course, I know why there should be a limit, or why I should think there should be a limit, because of the exchangeability argument.
Right.
Yeah.
So you're saying that because of erosion and wear and tear,
it
just doesn't exist in the limit.
Oh no. Well, point one. Point two, you just can't get to infinity because the universe will end. Point three, why should I, if I think, what do I mean by the limit? Okay, what I mean by the limit, I don't mean it definitely will reach a limit. I mean it will be by the limit in probability. What do I mean by the limit in probability? Is that a relative frequency? Do I now need to think about a whole sequence, an infinite number of sequences of an infinite number of tosses, and look at the proportion of those in which that reaches a limit? And
kind of a delicate argument for us unwashed engineers. It seems kind of a delicate argument, isn't it?
Yeah, but the point of it is because this is what really is, because the exchangeability argument is so natural. And so the reason that I make the distinction is that in the bucket, it's clear what that proportion P is.
Sure.
Yeah. There's no question about it. There's nothing in a sense to discuss. We can discuss whether we're picking them out in a truly random way, but the meaning of P is well defined. Yeah. Okay. Now, once you talk about tossing the coin, already we pointed out, that I genuinely don't know what you may kind of think you know what you mean, but you can see that there are issues about this. Once we start linking it to, we're splitting the coin is the simplest thing that we could do. Imagine now we have COVID patients, for example, and we talk about the probability that these guys have COVID. Yeah.
But surely there is a reality of COVID.
Yeah, there is a reality that at this time point, I can write down everybody having, a state that would be diagnosed by COVID, were I to test them right now at this moment.
Right.
Everybody, and then in the next second, everything will change, and in the next second, everything will change. Yeah. And again, this is a statement about the relationship between this is where the bucket is actually very informative, because what we mean by the probability, in fact, is your judgment about the collection of there's a collection of real things from which you are now subsampling. Yeah. And right now, you see, you are basically making the exchangeability judgment, and it's so natural. But you're confusing this exchangeability judgment. But of course, because in fact, the fact that that I've told you that they're exchangeable to me, okay, doesn't mean that physically that people are picked out according to this thing. When I told you about the spinning the coin, there's Dave, and then there's Judy, and then there's Susan, who may or may not have COVID that I'm testing. Okay, then these are not coin spins. Yeah, were I to know in more detail, then I would know that in fact that over the weekend, which I haven't got the weekend written down, in fact people are more likely to test positive because just because of how the process works. The system. In fact, I didn't actually tell you that there are two different hospitals testing these things. Yeah, and the hospital one hospital is really good at testing, the other hospital is really bad at testing. Yeah. So the more I learn about these things, the more I think, I don't need, it's not, like these things. However, at an exchangeability level, until I actually have this information, it's the information that my judgments have to work on that creates this. It's not that truly physically, there is a process which truly physically reaches a limit. So in one case, I had this hugely complicated thing, which you can say, well, you're trying to say, well, never mind that, I'm an engineer, I'm too busy. Or I can be very precise and say exactly what I mean.
I have 2 more questions, if we don't mind, before we move on to the discussion.
Yeah.
Alex, would you like to read out your question?
Yeah, sure. Sorry, I apologize if there's like a hum in the background. I don't know how obnoxious that is, but
it's okay. It's not at all.
Yeah, it was basically just asking for a bit of elaboration on the temporal short preference. Just wondering what the specific detail that provides is. Because if I know for sure something, then temporal short preference obviously suggests that if something is certain, you shouldn't ever believe it's impossible.
Okay,
but presumably it provides some sort of detail more than just disallowing belief in impossible things.
Okay, so remember that. Okay, so obviously I jumped over a huge number of steps here to get from temporal short preference, which is so remember what the logic is. It's a logic about my preferences. It's not a logic about something I know that, so the truth is that I definitely prefer A to B in the future. Yeah, okay. So now the point is that so how you might then wonder, does that, because remember when I write this down, I haven't talked anything about, there's nothing about temporal short preference here. Okay, all I tell you is that I have my uncertain quantity A, my uncertainty quantity B, okay, and I have judgments about A and B now. I tell you what P of A is, my P of A is. I tell you what P of B is. I tell you what P of A conditional on B is, okay, and at the future time, I'm going to tell you I am definitely going to observe B, and then I am going to tell you what my future probability for A is going to be at that point. So and I tell you that I obey temporal short preference, okay, which means that I don't disagree with sure things. Yeah, okay. So now my statement to you: if you think temporal short preference is very reasonable, okay, why wouldn't I agree with that? Yeah. Okay, then what I'm now telling you is, it's a bit like if I tell you exchangeability, you have to act as if you have aleatory uncertainties. If you agree with temporal short preference, and clearly there is a series of steps that goes on, there's a machinery that happens behind the scenes, okay, then you are going to have to prefer, you're going to have to relate your conditional probabilities are not the same as your posterior probabilities, but they have to be related by that equation. So, if I was only talking about temporal short preference, then I would unwrap that and I would explain. But informally, what happens is that I know in the future that I look at my scoring rules that lead me to preferring P sub T of A to any other judgment that I can make about P of A at that time, and by definition in the future I prefer that choice in various scoring rules. Temporal short preference allows me to pull that preference back to preferring that preference over scoring rules established now, and that allows me to open up my relationship between P of T, my future probability for A, now my judgments about it, and my conditional probabilities. So there are things going on behind the scenes here. But as I said, temporal short preference is a weak principle, yeah, which is why the fact that it has super strong value implications, I think is so interesting to me. Okay, it's a weak preference. It's so weak that you almost think, well, why wouldn't I have it? But why, given that, how could I even have short preferences? So why should that tell me about anything? But so your question really, I think, refers to how could that tell me anything? Yeah. And my answer is yes, it does. And if you go to the references, or if we were in the pub, I would write it on a piece of paper. I would explain what your short preferences are.
Okay.
And how they pull back. But it's not obvious from that. I mean, it's a theorem. Yeah.
Yeah, I think it's probably something that I need.
Yeah.
We need to sit down and have a read with. I think like it's perhaps for me, it doesn't feel so immediately obvious that it would be required due to things like, I don't like value discounting and things, but I think it's something I'll need.
It's not immediately obvious. That's why, you know, I have to write papers about it, and why come and tell people about it, and why you don't know it. No, I think it's very not obvious. And what is to me not obvious, and is that effectively that's all you need. Once you have this, effectively, you have the understanding about how your theory relates to the sort of, I mean, how theories of inference relates to real world inferences. Yeah. So, so when I came up with temporal short preference many years ago, and I thought, that's interesting. I wonder what I'm going to need to add to that. And I never found I needed to add anything to that. Temporal short preference on its own, which is such a weak principle, in fact, gives you everything you need. But so my point basically is you need something. I mean,
sorry, Michael, I'm just going to interrupt just because I would like to start the conversation. I know Thierry needs to leave at 12:30 as well. So thank you. Let's thank our speaker again, and hopefully we can continue that conversation afterwards as well. So I just would like to share a little reminder that apparently this is particularly relevant to this session. No biting, no eye gouging, no wrestling or hugging, no hitting below the belt, and vicious retorts are allowed. And the question to discuss is, can we agree on anything about handling epistemic uncertainty in engineering? Maybe Thierry, you could speak a little bit about that to start us off.
Yeah. Okay. Yeah, I think actually I agreed with quite a few things Michael has said, especially that that just building models of a real world reasoning. Maybe digging a little bit deeper, I have maybe two questions for Michael. I agree that there's no such thing as a objective probability in many cases. So I'm in for this subjective interpretation. But I'm wondering, in your view, for example, if we speak of a probability as a degree of belief of a specific individual, okay, do you think, for example, do you think probabilities are actually elicited? So it means that an individual has some in their mind, so some number, and we try to elicit that number, or are probability judgments constructed? In that case, it would not be anything like a probability, like a probability number in the expert's head, but this is just by the process of constructing the model that these numbers are constructed. What's your view on that?
Fine. Okay, so that's a very important question. Okay, so so I think my fundamental answer is, why do we have all of this theory? Why do we create all of these complicated models? Why do we do all of these? And that is to help the expert to make judgments in which they can have confidence and which they can explain to other people. Okay, yeah. So you can, so effectively, what I mean, I think there's two things: there's meaning and there's value. Okay, so a subjective probability, you can just be my subjective probability. You just ask me something, and I say, oh, 0.3, and then I can tell you what it means. You know, I just means that's my judgment. Yeah, but does it have value? Okay, so the fact that that was my 0.3, I mean, of what interest is that? Should the whole world suddenly change its entire behavior because I told them that my the thing that I just came out of my head was 0.3? No, it has value. Okay, because we can carefully unwrap the reasoning that we use to reach that in such a way that it's open to scrutiny. So when you said just a model, I mean, at that point, I mean, these models are hugely important. Okay, I mean, just like climate models are, you know, are hugely important to understand climate. I mean, it's important to understand that the climate model isn't the same as climate, but that's not to say we shouldn't look at climate models. It's to say we should very carefully build them, and we should very carefully understand the ways that they're not quite the same as climate. In the same way, the models for reasoning, hugely important, as long as we understand the differences. So my problem with elicitation, I mean, which it kind of is a field, is it tries to sort of essentially just sidestep this. I mean, so the elicitation from an expert is only interesting if that expert basically basically knows a lot already and has gone through this whole process and is very thoughtful and has basically looked at lots of models and understands all of these things. And even then, I would still want to support them so that their things had value. So if you think about meaning and value, the meaning can just be, yeah, but the value comes from all of these things that we do. And again, we should point out again that what we talked about is, I mean, if you think about the models that you wrote down, again, and I meant to say this, and with Mattis in the audience, I mean, it is a good time to say this again. Temporal short preference is not a thing that goes into base any things. It can influence basically any world of inferential reasoning. In particular, a lot of the imprecise forms, particularly probably more the version that Wally created, live naturally in all these things. And I said, and you can, and Mattis has written some very interesting things about that. Okay. But anyway, sorry, I got a bit sidetracked. Did I answer your question about my view on this? If you think about meaning and value, I mean, think about the two features. Yeah.
I wouldn't have worked on models of uncertainty for many years now if I didn't believe that these models have value and they are important.
Yeah.
The point I'm trying to make is I think for me these judgments of uncertainty are constructed, and the choice of a formalism like probabilities or other formalisms help the people to formalize and even to construct their judgment of uncertainty. And maybe where we depart is that I believe there are different languages for that make sense. And and another, because a related question is, okay, you say, and I agree with you, that these models of uncertainty are tools to allow us to help, let's say, experts to express their let's say uncertainty judgments. Okay, if you have, for example, some parameter of a model, and an expert is comfortable with giving bounds, like bounding the parameter by some interval, why would you force them to give, for example, a prior probability?
Mm. Okay, so there's two levels of this. Firstly, you might not want to do that. Okay, and as I said, I mean, and you can see in the chat, Mattis is kind of joining in on that, about that it's fine. You might want to just take this forward as your answer, okay, and that's fine, okay. I mean, but again, this is what a lot of this comes from where I came from. So remember, I started talking about you have climate models, you have disease models, you have energy policy for the next 30 years models, you have sort of natural hazards models. You're trying to model the whole universe, and I wrote down all of those 8 forms of different uncertainties that all need to be combined. Yeah. Okay. Now, once each one of these is a thing that requires a careful analysis. Okay. Now, once you start putting these things together, the more you just allow all of these things to be intervals, yeah, and then you push an interval, okay, on a particular, your view about how black holes relate to metal construction in the universe. Then remember, you have to push this interval through the galaxy model that takes on a big supercomputer. It will take sort of days and days and days and days, and you have to pay for that money. Okay, yeah, okay. And if you just had one interval, you could just about see how to push that through. Yeah. But of course, now every single thing in there is, has levels of uncertainty about that. Yeah. Okay. So the actual practicality of doing all these things, it kind of defeats you. Yeah. So this is where, again, I think when I put these distributions on, or when I put values on and put possibilities on, you know, I try not to overinflate that. It doesn't mean in some sense these are true. I mean, a lot of these things are pragmatic choices. Yeah. Okay. So what I then do is that I combine that. When I talk about my uncertainty, I think, well, you forced me to make these statements. Yeah. What is the uncertainty that like everything else about the model? You know, when I create my climate model, I simplify my judgments about, you know, about how does water behave? Because you told me that I can't do water point-wise. I have to do it on a square. So I'm going to have to fake water. You know, when you told me about this, you made me put something that went through this. Yeah. Okay. Now, of course, so that, like any other simplification, okay, introduces uncertainty about my confidence in the results. So my kind of answer to this is that I only force you because downstream I have many other things to do, and I need you to do this. But therefore, like everything else, you know, I now have to carry, you know, this is the point about you. You can use any model you like, but part of your job is relating that model and the things you've made to the real world statements I want to make that will cause people to do things. So when I force them to do that, yes, I need, and so again, some of the final references I put up about reified modeling, about structural discrepancy modeling, is about how I can take into account the extra uncertainty that I create by forcing people to do this. But I have reasons for doing that. Does that kind of answer in a roundabout way your question? Sorry, these are, because problems are complicated, answers are complicated.
Yeah. Okay, maybe we should let other people take part in the discussion.
Does anyone have anything else to add to the discussion? I believe Michael already read out Matthias's comments. If anyone wants to write anything in the chat as well, they're welcome to do so.
Yeah. And Matthias, do you want to put up the reference to that nice paper that, for Teddy's Festschrift, in case somebody wants to read how it works for that? Just in case anybody wants to, wants to follow this up anyway. So, or you can just ask Matthias afterwards. Yeah. Mm.
I'm kind of stunned by how agreeable Michael is being. You're willing to tolerate an interval as long as you don't have too many of them, I guess, right? So
yeah.
I think that is I mean, in this crowd, that's almost a concession. But I think it's helpful. And do you think, I mean, the great heresy that Peter Wally committed, of course, was not just introducing intervals and sort of creedal sets, but suggesting, I think, that there's this kind of uncertainty that ought to be treated that way, that's arguably different from what I would call a Laplacian thing that, you know, everybody agrees what you do with aleatory variables. Probability is the right way to go. But when it's epistemic uncertainty, sometimes you can treat it with with probability models, but sometimes it feels like you can't. What do you think about that?
Fine. Okay. So firstly, when I talked about being, I try as a subjectivist, I view myself trying to be non-judgmental in that way. If you have a model and you can convince me of something, then that's my subjective judgment too. The point I was making is that any model is just part of the story. And you still need to link that to a real world inference. And the reason that I prioritize subjective models the way I described them is that I can tell you how to do that. I can tell you, I can use exchangeability to fold in aleatory probabilities, which I really otherwise can't really understand. I can tell you why my conditional probabilities should tell me something about about my actual judgments. So you can do any model that you like, and that can be useful. But to me, the real use, I mean, you have to do that two-part thing. You need to then to make the bridge. And what I find lacking, but I'm not declaring you couldn't do it, just that I haven't seen where people do it, is really the principal statement about what that bridge is. Now, Scott, you asked me, you carried on, and because I kept chatting on this, I've forgotten, you asked me a rather more point is, oh yeah, okay. So when Peter Wally, for example, so I had many discussions with Peter Wally about this exact thing, about, you know, obviously you can say, I mean, that you have an interval because you just haven't got the time, the energy, because to actually reduce things. But the question about whether you could in principle reduce it, and whether you just haven't, or whether it's just is irreducible, I never understood the sense in which Wally was trying to describe that you couldn't. Because I said, well, supposing you did, what bad thing would happen to you? You know, I'm going to say that my epistemic uncertainty about the proportion of COVID people is between 1/3 and 2/3, you know, and then I'm not going to say anything more than that. And I said, well, supposing I just say it's a half, you know, because, you know, what bad thing will happen? What principle have I broken? Yeah, provided a half was my judgment, yeah, and my half was carefully reasoned, and that effectively I'd done a sensitivity analysis, because remember, when I take that value, I'm going to need to push it through. I mean, if I'm like in SPI-M, I need to push it through like 1 million further downstream models on what will happen if I introduce various restrictions. What is the difference between the compliance of this group and that group? What will happen, you know, how about if I make this kind of announcements about vaccine validity, you know, how will it differentially relate to the different groups? How much compliance will I get on lockdown on here? How does that relate to how I'm opening or closing the borders? Blah, 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 blah. So all of these things, this interval that I put in, okay, that I'm being a bit fastidious about now, yeah, you know, then this interval, I mean, is setting up all sorts of things for downstream, yeah, which, I mean, so I need to not be able to make it a half really, really seriously, because I'm really, really, really creating a world of pain. Because every one of these things, in fact, this thing about whether they have COVID is probably the least of it. I mean, all around this model, I mean, the models have zillions of parameters, all of which, you know, have their own uncertainties. Yeah. So I really, you need to convince me that I can't just say it's a half, or put a little bit of uncertainty around that, as put a probability distribution on and explore that, I think. And nobody's ever explained to me why I can't. I mean, I might not, but if I wanted to, I don't see why I can't, and what would stop me. I mean,
I'll try. Chris Rock is a comedian in America. He's sort of famous, and he says he describes the Chris Rock school of lottery investment. So the public lottery is the same as in the UK, and he says, you know, either you win the lottery or you don't win the lottery. Therefore, your chances of winning the lottery are 50-50 in his work. And with this investment strategy, you can make a lot of money. That's one of the bad things that can happen.
Yeah. Oh, yeah. But what you've now told me, okay, I mean, if we talk about meaning and value, the fact that Chris Rock says that doesn't necessarily mean that it has value. So, what you're kind of saying to me is just the same as if you're saying, you know, I say I'd like to model COVID, and you say, oh, Chris Rock had a very bad model for COVID. You've either got it or you haven't got it. Therefore, that means that modeling COVID is a bad idea. You know, and I say no. It just means that Chris Rock is not a good COVID modeler. And there's nothing that I said in any way that's meant to imply that any subjective judgment about anything is equally interesting and valuable. Just in the same way as I wouldn't say that any model of climate, they're all equally good. They're just models of climate.
Okay, well that's actually quite interesting. So how do we know when we've got a good subjective characterization and when we have a bad one?
Okay, so firstly, the question is it has to have meaning. Okay, is it a subjective characterization? Yeah, okay, so that's point one. And most fall at that point, okay? And then if it is, you then have to then unwrap why was it made? And this is why I was quite careful every time on those slides that I flashed up. You know, I said that, once you start talking about science, it's not the fact that it is the judgment, but it's a judgment for reasons which can be made transparent, communicable, and plus, etc. So in the end, I tend to feel that there's, that there is a residual uncertainty in all of these things. Okay, and the question is, how much does the science resolve it? and how much effectively is still left for don't know. Yeah. And so if that's all been carefully done, okay, and then the reasoning has been unwrapped in such a way that it is open for scientific scrutiny and peer review, then it's just as, you know, any other question in science. I mean, this is, you know, because it's a subjective judgment doesn't make it not part of usual scientific method. And this is my point. Yeah. And the questions you're asking are just the same as the questions you'd ask about any other aspect of science or engineering or technology or anything sensible. And
that seems to make sense, but I guess what we're talking about are what you call the actual real world reasoning, which I take to mean when you assign things truly subjectively and you don't really have the underlying model to justify it very well. Certainly we're going to be limited because we do have to use those sorts of inputs at some level, right? And you know, sometimes we have elaborated expert elicitation strategies, and sometimes we don't. But at some level, we're going to have some inputs which have this character that we don't have a good argument for them.
Yeah.
And in that case, I mean, maybe there you can't really distinguish the good from the bad because it, you know, depends on something that's not known. Maybe it's fair to say that you don't really know how to distinguish there, but I'm just curious as to what you think about it.
Okay, so let's pull that back a bit. I mean, is that different from, here's me, I mean, I need to apply a system to the world and I need to create models for it. Some of these aspects of these models are really well rehearsed. We've really done like loads and loads of these, really well understood. And some of these parts of the modeling I need to fit in because, well, no one's ever done this before, but I have to build the model for it. Okay, here's me looking at data. Some of this data is really, you know, really well collected and blah, blah, everything, yeah? And some of this data is, well, if we found it in the back of someone's envelope and it's better than nothing, but, you know, it's what we have, yeah? So, I mean, all of these things, all of these judgments, okay? I mean, it really is judgments all the way up. And when we talk about our uncertainty, okay, when you know, it's perfectly reasonable to talk about, you know, which judgments we're confident about and which judgments we're uncertain about. And the judgments we're confident about means that as we go downstream, we're pretty confident about, and for reasons we can explain, we're expert and it's good science and etc. and lots of data and blah, blah, blah. Yeah. For things that we're not, as we go downstream, we are going to be uncertain about the implications of what we say and the consequences. So, for example, we really don't know, you know, we're fairly confident if we let COVID just run, you know, what will happen. Once we start going into lockdown, we're much less confident because we don't understand what compliance is going to do and etc. If we have our borders firmly locked down, it's much easier to write down our models for what will happen once we open them. I mean, so effectively, our uncertainties have things that we're fairly confident about and things that we're not confident about. And in the subjective judgments, this is all part of it.
If I can add something, I think to me, I'm wondering if this comparison between like physical models, like climate models, and models of uncertainty, I think it's you can push it to a certain point, but I think it's not really absolutely correct because if you take a model of climate, for example, it's purely descriptive, whereas theory of uncertainty also has a normative role, and I don't think it has a value as being purely descriptive. I don't think it's so important to model people reason under uncertainty because we know they are subject to biases and so on. So it's one point, and a related point is you mentioned, Michael, communicability. I think it's a very important point, and I'm wondering if to some extent these let's say theories of statistical inference are not also partly kind of social construct. I mean, we agree that if we handle the problem that way, with that formalism, it's acceptable. Like, for example, take reliability analysis, for example. Okay, we agree, and this is very normalized. We agree that if we build a fault tree in that way, and if we elicit or construct the probabilities in that way, we agree that, okay, we have we have demonstrated that the, let's say the plant is safe. Okay, so I'm wondering if those different approaches to statistical inference are not also this kind of social construct. It's a set of, it's an accepted, reasonably widely accepted way of solving a problem, okay, in an acceptable way.
Yeah. Well, I think firstly, I think that I totally agree that these things have a big element of social construct, and certainly it is how these things work in practice. I think part of the reason for foundations is to open that up and say, is what people are doing, I mean, they accept that, but are they right to accept that? For example, okay, disease modeling. So I've done a lot of work with epidemiologists, okay? And so COVID has come along, but before that, you know, so a lot of work, other people in Durham who've done a lot of work on this. So we sit down with them. So, you know, as I said, I've shown you a bunch of different areas I work with. And one of the key parts of the problems is the fact that a model is a model and the world is the world, okay? Now, you're going to, let me just assert that every epidemiologist I've ever talked to says they don't have that concept in epidemiology. In other words, you write down your model, you see if that model can fit the data, and if it does, you use that to influence policy. Yep. So even though down the pub, they understand completely that the model is a model and the world is the world, what they say is nobody else worries about the difference. It's like the structural discrepancy, you know, that, you know, even if I got my parameters exactly right, you know, what would this actually say about, you know, if I did this following intervention, what would actually happen? They say the following. They say that if I started putting structural discrepancy in my model, that would be implying that my model wasn't as good as everybody else's model, because nobody else does it. So why should I do it? Yeah. So there's, you see, there's a social construct, and you see the damage that is caused by this social construct. So all of these COVID models that come out that people are following, and they're throwing in, they're determining what we should do, etc. The notion of a careful structural discrepancy analysis, which when you talk to individual epidemiologists, they say, oh, that sounds important. Wish we had time to do that. They're not carried out, and it's part of the culture not to carry it out. So it's very important, I think, I mean, to recognize that it is, to recognize that these cultures are not totally stupid. I mean, these people who do this reliability, you know, if every time these things were not reliable, they'd find out. And yeah. But then you ask, you know, the foundations is to ask, can these things be done better? You know, and yeah, and so that is a, you know, an important part of the argument.
Yeah, I agree. I definitely agree on the importance of foundations. Yeah, definitely.
Yeah. So I'm not sure we're kind of agreeing on everything at some about handling epistemic uncertainty at a level. Yeah.
I think Jasper wants to throw a Molotov cocktail on us. Jasper? Oh, he has it in chat.
Well, I could try and explain it in words, but I have my daughter here and it might turn into a big mess. So perhaps I'll try and let chat speak for itself, and then we see how it goes from there.
Okay, so this is again the question about supposing you really, really, really couldn't, okay? And then, so I'm just going to say, okay, let me just say that, okay, that well, I sat in many, many rooms with many, many people who couldn't, yeah? And then talked through very carefully, okay, the reasons that they couldn't, okay? And a lot of the reasons are to do with their confusion about what probability is, because they think that I'm telling them that probability is a real thing, and which they can't get their head around, or it's a meaningless thing, or whether they can't get their head around. So basically, we go through a very careful unwrapping of what they think it is that we're talking about and why they think they can't do it. And so again, this is the thing about experience and acceptable reaction. I've never yet found a situation where people weren't in the end actually happy to go with a judgment and to go with an analysis of how much we would need to vary that judgment in order for them to have some kind of confidence that the overall statement, which remember, I mean, very much the thing I keep emphasizing is that you take this thing through a subjective analysis. That doesn't mean that's the answer. Everything I said is that there's a formal analysis, and then there's, if you like, a structural discrepancy that relates to the formal analysis I've carried out. with the value they've fixed, that isn't the answer that they believe. There's extra uncertainty that we've introduced that needs to be added on, that we've found a way through to do it. Okay, so I haven't yet found this problem where I couldn't actually do it. So that means what makes it, and remember, I've done this, for about 50 years, I've been doing these things. Yeah. So it may be that I just trick people, or I just get tired and they say, fine, 0.3, can I go now? And I can certainly imagine this could happen. But to me, I think a lot of this is to people not understanding what the language means and what the task is and how this relates to the answers they're going to get. Yeah.
That extra uncertainty that you have, that you treat along with it, that's in the form of a sort of a Bayesian sensitivity analysis. Is that right?
So sensitive analysis is clearly a part of this, yes. But of course, what you need to do, and this is where a lot of these references are, is that having done the sensitivity analysis, you still have to wrap it up in, not just saying, oh, this model is sensitive, but now I want to then take it to a decision analysis, and the decision analysis has to handle all of these things. So if the sensitivity analysis, I mean, it may just nail it. It may say, well, and very often we talk about decision support, we can say that, that it is sensitive to that this decision, is pretty safe, all over that, and that one isn't safe. So, I mean, all the common sense things about sort of informed decision support, is relevant to this. But sometimes you just need to go further because it's just complicated. Because like you're trying to run a real-time energy system, and that real-time energy system, it's going to need to know what the energy requirements are likely to be given climate for the whole of the next year, and you have planning options. You could do this, that, or the other, and to a certain extent, you just run out of your ability to be sensitive, I guess. So the notion of putting a value in, putting an uncertainty in, and then doing one of the other things that I suggest doing then becomes attractive. But again, a lot of these things, they are very problem sort of restricted. And again, see, I'm not really dogmatic about this. You should do whatever you're able to do, but you should be very careful about explaining how what you did was relevant to the problem that you had. And so my issue is simply, have you said carefully what you meant, and have you justified that you've given value to that meaning? And if you've done that, well, that's fine.
A question to that, isn't it possible to have different values associated with different ways to understand probabilities? Like, for example, if I have I like a loaded die, because to me, that's the simplest case of an interval analysis. I'm going to roll a die, and depending on its outcome, I'm either going to shoot you or give you $1 million.
Yeah.
You can have as many subjective people come in and say, oh, well, I think the probability of the outcome is going to be whatever, but it's loaded die, so you don't know. Yeah. But to me, there's also something to be said for, you could have more confidence in the interval bounds of something than you could in any individual probability of it. And so while you say, oh yeah, I think the answer is 0.3, but I think even more, the answer is going to be between 0.1 and 0.9 or something. And then, I mean, a lot of our methods can't actually, I'd say, use that type of analysis, but to me, they need to be able to, because you almost have higher degrees of confidence in intervals of things often than you do in any specific probability, even then when you run like a sensitivity around that value.
Yeah, no.
Audience is saying the same thing in his chat question as well. That sometimes that sort of ambiguity or uncertainty or residual thing that's left makes a difference, that we have to recognize it, an indecision about the decision.
Yeah, so I think that the notion, yeah, I mean, all of this is fine. If that's the analysis you did, and that's what you go ahead and do, okay, yeah, okay. And it's fine for you as the decision analyst to say, this could be good or that could be good. Yeah, okay. Now, the question then comes for the person who actually makes the decision. Yeah, so they say, okay, thank you very much. I listened to that, and now I'm going to do this. Yeah, okay.
See, Michael, that sounds like a bit of a cop-out. I've been reminded throughout a lot of this discussion about a nice anecdote that Gerd Gigerenzer gives. I think he's speaking later in the ViCE talks, where he talked about one of his colleagues that had a major life decision to make about whether they were, let's say it's a female colleague, and they were deciding whether they were going to marry this guy or not. And this guy happens to be, I don't know, great in bed, but a really bad drinker. And so he turns to his colleague and he says, well, you teach decisions, so just do the expected utility, and then that gives you the answer. And his colleague turns to him and says, come on, this is a really serious situation. And so they'd never use those applications. It sounds like your answer to attempts to get estimates that might be the type that Thierry's discussed, or some of the other colleagues on the conference. It's a bit of a cop-out to just say, well, in really serious situations, the decision maker is just going to do what they want anyway. They don't need to worry about it.
No, that's not what I said at all. What I said is that you do what you can, and then you report honestly what you've achieved. Okay, yeah, okay. Now, the question about whether I mean, if all that you've achieved is to point out that if there's any way you can get out of this person tossing the coin and then shooting you, then you'd like to do that, then fine. Yeah. I mean, oh, well, not fine. I mean, it may not be very useful, but that's what you've done. Okay. So now, so the caveat that I always make is, because this is what always happens, okay, is that the decision analyst is actually quite careful. You know, the COVID people have done their analysis, and they've written somewhere, they've put a footnote on page 47 of their report that said, of course, it's only a model, it makes assumptions, and it's not that you should believe it's a model, assumptions, etc., blah, blah, blah. Okay, and then they put their conclusions, and then they say, of course, this should be done, taken into account with the assumption, etc. They then pass it over to the decision maker. So the decision maker knows nothing about the model, knows nothing about the caveats, knows nothing about the sensitivity, is totally untrained in decision analysis. Okay, yeah, okay. So the reason that I would actually say rather more strongly that it's better to force the decision, even into areas you're uncomfortable with, is that otherwise you're passing it to somebody who knows less than you do, who knows almost the qualification for becoming the person who makes the decisions is that you know nothing about decision theory, and you have no understanding of how good decisions to be made. You certainly have no understanding of the science. Giving it to them and just saying, you know, that you've been very clear about what it means and what it doesn't mean, I mean, keeps your hands clean, but in fact, it just creates problems downstream. So that's why I always say, you know, that you should, in fact, push to the point where you're actually making a recommendation, but you're honest about the limitations of that recommendation. So I don't think, no, I wouldn't cop out. In the example you gave about the person who's drunk and the person who knows nothing, that's just a good example of the fact that, that things have meaning and they have value. If somebody who's clueless and useless goes through this things, then what they give will have meaning, but it will have no value. And I'm not advocating for doing things that have meaning but no value. Did that answer your question? I'm not sure it did.
I would say I think that's very reasonable. I think the other thing that to me is also very interesting is usually when you make decisions about modeling based on models and simulation, the results of the model is only part of it. Mm-hmm. And so, I mean, I do agree with you're generally handing this off to some manager that doesn't have as much information as you do. And so you have to construct the results of my model give me this, even with uncertainty, I have this, but then you create another logical argument about why I think X should be the correct path.
Yeah.
And I think I agree with that.
Given that Thierry is no longer on the call, I think it'll be a lot easier to find things we agree on. I suggest say what you mean, report honestly what you found, and intervals might be okay, but are often computationally intractable.
So let's now be honest about saying what you mean and reporting honestly what you found is tricky. I mean, let's not, I mean, in the sense that, for example, if you ask a COVID modeler what they mean by their statements, what they actually mean by them, there will be a whole bunch of weaseling. They will not say what they mean. I mean, and
You need to hold their feet to the fire. It's a hard process for sure.
It's not even that you need to hold their feet. They just haven't got a culture of these things actually. I mean, their meaning is, we just have a modeling. We have an acceptable set of things that we do. So it was like when we talked about climate earlier on, that climate exists. So I've been in several climate meetings, okay, and it's very clear that climate scientists have totally different views as to what they mean by climate, whether it is average of 10 years of weather, whether it is an implicit unobservable stochastic process, whatever. So in each of these meetings, because I tend to go to more foundational ones, I said, let's have a breakout session where we just nail what we mean by climate. Okay, and there's always some old guy who says, there's no point in doing this because you're just going to get grumpy and you're not going to reach any conclusion at all. And they're always correct. I mean, they don't reach any consensus. So the notion of saying what people mean, it seems simple enough, but you unwrap it. And this is why, saying what you mean is huge, actually. It's, and why I so much emphasize, the notion of exchangeability is a thing I can say what I mean by it genuinely, and that makes my notion of where I brought aleatory in exactly. My notion of temporal short preference, I can say what that is, even though it seems weird to people until the first time they hear it, but I can say therefore why I thought this model related to actual judgments that I make. So saying what I mean is actually a big deal, I think. It's hugely important.
I totally agree, Michael. And it's not just at this foundational level either. And even in practical terms, people aren't saying what they mean. For instance, people sometimes show error bars on graphs and have no idea. No, you can talk to them. They have no idea whether they're showing standard errors or standard deviations. I mean, it's quite remarkable that they couldn't tell you the difference.
No. They're just what everybody else puts on.
Yeah, exactly.
Yeah, yes.
So Thierry disagrees that intervals are necessarily more intractable.
Well, I'm not sure that they're computationally intractable when they're computationally intractable.
Yeah.
I'm not making a statement that they will be.
Yeah.
But as problems become more complicated and have more and more sources of things, and you more and more would like to put intervals on.
So do others see any? Well, I mean, is there anything we can agree on about epistemic uncertainty or uncertainty in general with an engineer? Are there things that we can say we believe as a community? I'm thinking of people who've I see a lot of names but very few faces in the among the attendees. Does Jesper, do you have any thoughts? Roberto? Or are we swimming in this controversy and we like it?
No. I think the thing we agree on the most, I would say, is that it's very important to say what we mean. Funnily enough, I have the impression that we don't really agree yet on what we mean and what we ought to mean. And that's what kind of the debate is about. So I find that an amusing takeaway from this debate. If I then pinpoint it, for example, the whole thing we start from, are they numbers, are they intervals? And no, we can always reduce them to numbers. No, we can. So this to me is very much intertwined with what does that interval or that point value mean. Sure. But so funnily enough, we have that debate, not settling at all. Yet we are all very happy amongst us to discuss it and have the debate. And I think that is, to me, that is very nice about what's going on here. But it's definitely not settled yet as I see it, as to what it means.
But let's clarify this. The reason I don't want to say you need to clarify it is because there could be different meanings that would genuinely have value for different purposes. So that's why I think that it's not that there is a correct meaning. Yeah. But each meaning that you have to say what it is and for what purposes can it be useful. And I'm just saying that the subjectivist things, I can say what it is and what purposes I think it's useful. I'm not saying that you might come along and tell me something else that you could give a meaning for that could be useful in another way. Yeah, and that's kind of like the people who like that. That's kind of their job. But I'm not denying that you could do it. You know, I'm not saying that the controversy needs to be resolved by one. There is one meaning that has one use. Yeah, and it's quite feasible to me. It's just I don't know what these other meanings are, and how they're justified. But that's okay. I'm not denying that you might be able to do it.
Yes, I definitely agree that there can be and should be multiple meanings, and that they all have their own uses. I'm not convinced, though, at this point how the particular meaning you seem to use is always applicable, but which you kind of seem to suggest. But okay, I don't want to reopen the debate. I don't know.
So obviously, no one has ventured to suggest that uncertainty analysis is not just intrinsically useful. I'm sure this is a self-selected population, so nobody has this errant opinion. But certainly within engineering and elsewhere too, there are plenty of people who do not believe in the intrinsic importance of uncertainty analysis. I think, I mean, I presume that we all agree that there is some value to exploring our lives.
Do you mean there's no value in the things that they do, or there's no value more generally?
I think more generally, there are plenty of engineers, for instance, who don't use uncertainty analysis of any kind, who use point estimates and are happy with those and don't really see the point. I mean, they'll do sensitivity analyses maybe, but they will not do a distributional study of any kind.
So you wouldn't want them to get anywhere near COVID planning, would you?
I agree, but as you said, the epidemiologists are another camp.
But the epidemiologists, they do think about uncertainty. I mean, this is the point. But what they think of is that they've built agents, model basic things into their models. So they think they've folded uncertainty enough into their models. Yeah. So these agents womble around and meeting people or not.
Right. They have what the ecologists call demographic uncertainty, but they don't have, you know, uncertainty about testing, for instance. They don't include at all.
Well, but if they think that the idea is that they put everything about uncertainty into their models. So if some people are tested and some people aren't, and there's a differential bias, in principle you could feed that into your agents. So I think their argument goes in two steps. In principle, you could do this. I haven't actually done this, but in principle I could have done. So let's say I did, while knowing full well that I didn't.
That's right. I want credit for it, even though I didn't do it.
Yeah. So this is between talking to people down the pub and talking to people in the professional context, where they have to follow, it's like the rules of the game.
May I add also, Scott, to your points, and I take the opportunity to thank Michael for the very interesting talk and discussion, but I would also argue that the sophistication of the analysis plays a big role. So, for example, in the model of the universe or COVID, I mean, we have plenty of data, we have plenty of modeling, and so on. But in real life engineering, you have to take a decision when you don't have data, and simple models like rule of thumb and things like that needs to be considered, and no data at all are available. So you have to decide whether that structure will support that temporary construction, and you have to make a decision. You have to be very sure that decision is the right one, because or workers' lives is at stake, and you have to make a decision with time constraints. So you can't make, you can't build a model of dependence. You can't build sophisticated model with data. You just have to make the right decision with time constraints. So that certainly has to be in the picture, right?
Oh, absolutely. Firstly, about COVID, I mean, there seems to be a lot of data, but in fact, there is never the data that you need. And certainly, if you think about the early stages of when people were making decisions, they just did not have the data. And whether they have the data now, I mean, is an interesting question. And I mean, all of these things, you are doing, you have not got the data that you need. You have to, everybody wants more data. And COVID is such a good example of working against extreme time pressure. I mean, the guys with their models, I mean, the government rings them up on the Friday night and says, look, we need to take a decision on Sunday. I know you haven't built this into your model yet. Could you please? Yep. Now, my answer to that, firstly, is that one of the reasons I emphasized that probabilistic modeling, is a model, but is not really up to the task, is because it's so detailed that you cannot, that creating full probability models is just too time consuming and hard. I mean, I actually advocate Bayes linear modeling just because it is so much faster and easier and actually better able to do the job. Okay, point one. Point two, even though time pressure is an issue, that's often used as an excuse for bad planning, in the sense that for COVID, for example, I mean, that the day that the epidemic was announced, or even before epidemics were, people knew that pandemics were a chance, there should have been a huge effort in creating the kind of flexible modeling structures that would have allowed people to actually to populate them quickly and to do stuff. So in your problems, it could be that something's happened that was entirely unexpected, that had never occurred to people. But often it's the case that people just haven't built the model, not that they couldn't have. So they're forced to make a fast and not deeply thoughtful decision because they haven't invested up front in careful modeling that will allow them to deal with the crises as they occur. And that's a huge issue.
Yes, that's I think very likely the case. Yes, I think so. That's a very good answer. Yeah, absolutely. I mean, I cannot disagree with that. Yeah.
Okay, are there any more questions to wrap up the discussion? Okay, it seems not. So I'd just like to thank our speakers again, Thierry, who's not here, unfortunately, and Michael, and everyone that contributed to the discussion. Thank you very much. Our final, sorry, not our final, our next talk, in fact, see whether I can just go back a bit, will be on Wednesday at 4 o'clock GMT with Yakov Benheim on innovation dilemmas and info gap perspective, and Francois Emez, uncertainty numerical simulation, does it matter, and what to do about it. And we'll be discussing, are there other kinds of uncertainty? So thanks again for everyone for attending, and we'll be uploading the talk onto YouTube and the Risk Institute event page for this conference. Thank you for tuning in, and enjoy the rest of the day.
Let's ask a question before we go. Is there an attempt
Sure.
to bring all this stuff together? I mean, the one thing, I was quite cool having this online, but there is a thing, if we were at a meeting all together, we'd sit there and we go to this talk, go to that talk and stuff, and things would knock backwards and forwards. So is it, I mean, I can understand totally why not, but is there an attempt to make this a unified thing at the end?
As in to have one big discussion at the end?
No, I just meant that, I mean, obviously each session has its own value and interest. But obviously these are not random sessions.
There has been some discussion of proceedings, and Sebastian Desterck, for instance, asked if there were going to be proceedings, and I suggested that that would be a great idea and that he should be the editor of the proceedings, but he quickly stopped talking to me about it. I think I don't. We have no provision for an ongoing discussion, but part of the point of this session is to have these people who are just names at least virtually meet one another and be familiar enough that they could send emails across and continue the discussion, on their own. We don't have a provision for a collective discussion, but maybe we should.
No, it's fine. I was just asking because it seems an interesting set of discussions to have.
I totally agree. I totally agree. And I do think that there's more that we could say about what we agree on. I think maybe some of that will become clear as the other ViCE talks sort of play out.
Yeah.
And I think maybe on the final session or something, we could have we could potentially share a drink and have some breakout rooms of smaller group sizes to try and stimulate some further discussion and kind of cycle through or something like that. So there's definitely room for more discussion, I think, that we could try and stimulate.
I have
sessions.
purchased some champagne since from before the COVID that I was looking to share, but I could just drink and become drunk in concert.
You know that that's the next iteration of Zoom is where you can share drinks over it.
Right. There is a rumor that someone is developing sort of smell-o-vision, where you can exchange smells across the internet. But I think this is a terrible idea, and they should stop doing it immediately.
All right, so let's wrap up. I'm sorry I have to go because I have another meeting as well. But thank you again for everyone for attending, and hopefully we'll see everyone on the 17th as well.
Fine.
Thanks, Michael. Thanks, Francis.
It was a pleasure.
Thank you.